Hello. Hello. Am I audible? I think I should be audible. Okay. So I will cover PPT 10 and 11, and I will be unlisting this live stream. So you might not be able to find it directly on the channel. So I gave the link in the group in case someone wants to join the live stream. Okay, fine. Sequential circuits. I don't think you would have to like master the previous topics to know what is in sequential circuits. So I think you should be fine. If you have the basic idea as to what happened before this topic, you should be fine. So basically, latches and flip flops. Flip flop is like a storage device, it stores a bit, and latch is the basic version of a flip flop. So we will go through everything now. And combinational circuit is basically you have all these AND gates, OR gates, and basically you make a circuit with that. In sequential circuit, you have something called the feedback. So we will look at an example, then maybe we'll understand. You have feedbacks and you have clocks and all those things come into the picture when we are talking about sequential circuits. So single bit storage is flip flop, and the basic version of a flip flop is a latch. So we'll see. Okay, this is like what is sequential circuits. So if you have a combinational circuit, wait, I can write on this, no? No. Is this writable? Yes, I can write on this. Yes. So, oh, I can't erase this. Oh my God. So combinational circuit is basically you have your AND gates, OR gates, and all those things. So you have this feedback system. So once you have a feedback system to your combinational circuit, it becomes a sequential circuit. How do you give a feedback? You're supposed to I can't erase this, fine. You're supposed to store, let's say you're at a certain state, so you store that state and give it as a feedback to the next clock cycle. So that's where the clock comes in the middle. So this is all just theory. I don't think there's nothing much to think about here. It's just that in sequential circuits, oh my goodness. 1 minute. Okay. In sequential circuits, you have a feedback system, and in order to store the previous state, we have flip flops. So flip flop stores the state. So what is a flip flop? It just stores one bit. So one bit is either a 0 or a 1. So those are two different states. Okay, fine. So the clock basically tells you, like, now you change, now you change, now you change, now you give the feedback, now you give the feedback. That's how it works. It is synchronous, so keep this in mind. So it doesn't, the clock, it keeps fluctuating periodically. It's not random, it's not asynchronous. There are other inputs we will look at, those will be asynchronous, will like clear, preset. I think they will come soon, so we'll see. Fine. So cross coupled inverters. So this is the most basic version. What does this do? It stores either 0 or a 1. So it's a bit storage device. It's storing a bit. Cross coupled inverters. Cross coupled inverters because you see a cross and then you see two inverters and they're together. They're coupled together. So cross coupled inverters. So basically, if you look at this, if I put 0, let me use a different color. If 0 is here, let's see, 0, 0, 0, 0 is here. Inverted, so 0 becomes 1 because of inverter. 1, 1, 1, 1, 1. 1 becomes inverted 0. You see, this is a continuous, it's a closed loop. So if you give 0 here and leave it, this device will remain as it is. So essentially, you're storing the state. Here you will get 0, here you will get 1. In theory, it will remain like this forever, but in real life, leakage of charge or whatever could happen. But in theory, this will remain as it is forever. For an infinite period of time, this will be 0, this will be 1. unless you change it. So let's say you gave here 1, so this will always remain 1, this will always remain 0. So this is cross coupled inverter. It is a bit storage device. It is storing 2 bits. If you put 0 here, this will become 1. If you put 1 here, it will become 0. Nothing else you're doing. You're simply storing data. What data? 1 bit you're storing. Fine, that is cross coupled inverter. Now let us upgrade our bit storage device. I'll still store the same bit, but now differently. I'll have some more control over this. Let's see. I'm using 2 NAND gates. I have, instead of inverters, now I have NAND gates, and I'm introducing 2 more variables, S and R. So they're like input. I can control what S and R are. S can be 1 or 0, R also can be 1 or 0. It's up to us. So the inverter became NAND gates, and now you have 2 inputs extra. So this is how it is different from the crossed coupled inverter. You got something that is called an SR latch. So latch is nothing but it's a bit storage device. It either stores 0 or a 1. So that's it. There's nothing much to latches. Truth table, let's see. See, essentially what I want to accomplish is, when I give Q here, I want Q dash in the other at the bottom. If I give Q at the top, I want Q dash at the bottom. I want complemented values. I don't want both of them to be the same. I don't want both of them to have the same values. They have to be complementary states. If Q is here, Q dash should be here. If Q dash is on the top, Q should be at the bottom. That's how it's supposed to be. So keeping this in mind, that I want complementary states at the top and the bottom, let's see what will happen if I give inputs to S and R. So if S is 0 and R is 0, what will happen? 0 and anything will give me 0. So you'll get 0 at the AND, but here not is there since this is an NAND gate. So 0 and anything gave me 0, and not of it is 1. So here you'll get 1. And if R is also 0, let's see what will happen. If R is also 0, 0 and anything will give you 0, and not of it will give you 1. So it is verified. So it doesn't matter. So 1 comes here, 1 and 0. So you check this. So 1 comes here, no? 1 and 0 will give you still 0, and its not will be 1. So this will continue. If S and R are 0, Q will be 1, Q dash is also 1. I mean, now this is not what we want. If Q is 1, Q dash has to be 0. But if S and R are 0, it is turning out that Q is 1, Q dash is also 1. So that's a problem. So we are calling it the disallowed state. We do not want this kind of behavior. So we will not keep S and R as 0 at the same time. We do not want this behavior. That's why it's called disallowed. Okay, fine. Other values, I think they are understandable, I guess. Let's see. S is 0, R is 1. Okay, let's see what happens. If S is 0, here 0 is there. 0 and anything will give you 0, and 0 not will give you 1. So Q becomes 1. If Q becomes 1, it comes here. And what did I tell? R is 1. If S is 0 and R is 1, no? So 1 and 1 will give you 1. 1 not will give you 0. So Q dash is 0. 0, 0. Now again, if you check, 0 and 0 will give you 0. And 0 not is 1. So everything is fine now. This is how it will remain for the rest of its lifetime. 1, Q will be 1, Q dash will be 0. As long as S is 0 and R is 1. That is what is here. If S is 0, R is 1, Q is 1, and Q dash is 0. It is called the set state because whenever Q becomes 1, you call it the set state. Whenever Q becomes 0, you call it the reset state. I mean, now I think it's understandable. Now if you put S equal to 1 and R equal to 0, the reverse happens. Q becomes 0 and Q dash becomes 1. Nice. Simple truth table. And if both of them are 1, what will happen if both of them are 1? If both of them are 1, what will happen? So let's see if both of them are 1, what will happen? Here this is Q dash, no? Q dash will come here, it will be Q dash. And this is Q, no? Here Q will come and it will be Q. So 1 and q dash will give you q dash. Its not will give you q. Not of q not is like complement of q complement is what? Q. Here let's see what's happening at the bottom. Q and 1 will give you q, q not will give you q dash. So what is happening here? You're not getting 1, you're not getting 0. Essentially what is happening is whatever you had previously you had q, the same thing is being retained. So q becomes q. It means you're retaining the value. It is a memory state. You're storing it. There is no change. So in place of q, if 1 is there, it will remain 1. If q was 0, it will remain 0. So it is the store state. Essentially what is happening is nothing, there's no change. It's a memory state. There is no change. That's it. This is SR latch. Here, compared to the cross-coupled inverters, here you have more control. You can give inputs to S and R. Nice. So you have 4 states. One of them is disallowed. You have set state, reset state. I mean, some of you might be thinking, does S mean set and R means reset? Kind of, but not exactly here. Here, if S is 0, it is being set. Like when R is 1, it is being set, and if S is being 1, it is getting reset. So it's counterintuitive. But we'll see. We will see in the later latches. We will see. There what will happen is when S is 1, you will get set state, and when R is 1, you'll get reset state. Which is not the case here. So we will wait until that comes. Here it's counterintuitive. If S is 1, it is reset. If R is 1, it is set. So if S and 1 both are R, you'll get a memory state. If both of them are 0, then we do not want that. It's not allowed. We don't want such kind of behavior. Okay, now we're upgrading. Now we're introducing one more variable that's called C. You can think of it as the control input, or slowly we will be calling this as the clock. We will come to that. Or you can call it the enable input, call it whatever you want, control, clock, enable, but this is some extra input. And how is it different from SR latch? This was there. I think there's only one addition, no? What is it? Oh, you got 2 more NAND gates. So what used to be a simple SR, now it got extended. You added 2 more NAND gates, and then you bring in another input called C. And this, in this slide, it's called control input. So what changes does it bring? I mean, you can always start with the truth table and see what's going to happen. All the combinations you can try. Let's see what will happen when C is 0. If C is 0, you get 0 here, 0 here. 0 and anything will give you 0. And 0 not will give you 1. Okay, that's the first top part. So here also, bottom also, 0 and anything will give you 0, and 0 not will give you 1. Fine, we got our values here. We got 1, 1. What about this one? What does this have? Let's see. We have a feedback, no? Here Q will come here. Let's say Q is the current state. What will happen in the next state we'll see. So Q is here. Q is coming as an input. So Q is here. Q and 1 will give you Q. And Q not is Q dash. Here also feedback is there. No? Q dash is going back. So you'll get Q dash here. Q dash and 1 is Q dash. But it's not is Q. What does this remind you of? The memory state. Q is becoming nothing but Q. So there is no change essentially. You're retaining the value. It's a memory state. So when C is 0, irrespective of what S and R input values are, your Q will not change. So that is why in the truth table, whenever C is 0, irrespective of S and R. So what do you mean by irrespective of S and R? You don't care. You don't care what S and R are. Whatever be the values of S and R, it doesn't matter. When C is 0, you get no change in the state. Q will remain Q. Q dash will remain Q. For example, if Q is 1, Q will remain 1. Q will not change. If Q is 0, Q will remain 0. Fine. That is when C is 0. What if C is 1? If C is 1, then it's interesting. I guess you'll get. We'll see. When C is 1, what will happen when C is 1? Let's say C is 1. Here you'll get 1. Here you'll get 1. So now you'll have to check what is S and R. Let's say what is the first one here? 0 0. If S is 0 and R is 0, what will happen? 1 and 0 will give you 0, 0 not is 1. 1 and 0 is 0, 0 not is 1. Now it's becoming the same story, no, as before. Here you got 1 1 means somehow, and look at this. This is like this part of the SR latch with control input is basically your SR latch. And if S and R are 1, what will you get? You'll get memory state. So there is no change. Right? This is not. Oh. Here, if you get 1 1, it's the memory state. So there is no change. But here S and R are different. Here S and R is directly connected to the NAND gates here. But here your S and R is connected to the outer NAND gates. They're not here. Okay, I think I can simplify it. I don't have to go through all this. I'll show you one way. Instead of going through all the combinations, let me write this as S. This is S. This is R. So S and 1 will give you S. R and 1 will give you R. And S naught will give you S complement. R naught will give you R complement. Now it's interesting. Now you can put whatever values you want. And you can check. You'll get the truth table. There is, it's not complicated, is it? If you put S as 0 0, here you will get 1. Here also you'll get 1. And here if you get 1 1, it's the memory state. If you put S as 0, if S is 0, S dash will become 1. And if R is 1, R dash will become 0. Now let's see what will happen. If R dash is 0, 0 and anything will give you 0, and 0 not will give you 1. Feedback will go as 1. 1 and 1 will give you 1. 1 not will give you 0. Feedback will go as 0. Okay, fine. So here everything is there. What is the final thing? Q becomes 0. Q is becoming 0. And Q dash is becoming 1. Now what does it mean when Q becomes 0? It means it's the reset state. Whenever Q becomes 0, it's the reset state. And when did Q become 0? Q became 0 when R became 1 and S became 0. So now here it makes sense. R means reset, S means set. So when R becomes 1, that is when you reach the reset state. The opposite is also true. When S becomes 1, you get the set state. You can try it by yourself. This is true for the SR latch with control input, but without control input, it's the opposite. When S becomes 1, it's the reset state. When R becomes 1, you can look at the truth table. When R becomes 1, it's the set state. So it's counterintuitive here. But here it makes sense. Here, when there is control input, it makes sense. R equals 1 is reset state, S equals 1 is set state. You can try all combinations. You can see, you can get the truth table here. This is the truth table for SR latch with control input. And all of this happens when C is 1. If C is 0, then there is no change. Whatever be the values of S and R, your Q will remain as it is. If it is 0, it will remain 0. If it is 1, it will remain 1. Right side of the... See, that's what. This right side part is there. No, it's exactly your SR latch. Here. Same thing. Let's see. Okay, now another kind of a latch, it's called D latch. It is very similar to this. It's like a special case of SR latch, or if you think of it that way. So essentially what you have here is this part is your this part is your SR latch. Now what you do to SR is S is there as it is. You give R equals to S complement. Then it becomes your D latch. Or in other words, I can say in SR latch, if you give S as D and R as D complement, it becomes your D latch. Because this entire thing is essentially your SR latch with control input. This thing is essentially your SR latch with control input. Now, especially what you're doing is At S you're giving D, so D is going like this. And to R, what are you giving? You're giving the same thing but complemented. So here you will get D, here you will get D dash. So essentially your SR latch with the control input, but now S is D and R is D dash. Now what are its implications? What is going to happen? Let us see. If control input is 0, you all know there is nothing is going to happen. There is no change. It is the memory state. Because 0, if C is 0, 0 will come here, and 0 and anything will be 0, 0 naught will be, it's the same story. 0 naught is 1, 0 is here, 0 and anything is 0, 0 naught is 1, and the same story continues. You'll get memory state, no change. What if C is 1? If C is 1, 1 will come here, 1 will come here. Now let's see, what if D is 0? If D is 0, 0 and 1 will give you 0, 0 naught will be 1. Okay. And what will happen at the bottom? If D is 0, D dash will be 1, 1 and 1 will be 1, 1 naught will be 0. And if you look at this, this is nothing but your plain old SR latch, your original SR latch without any control input. And what happens when S is 1 and R is 0? You remember? We've discussed. It is reset. In SR latch, if S is 1, you get reset. And if R is 0, and if R is 1, you get set. So it's the counterintuitive way. It's the opposite way when we simply talk about SR latch. If you remember, we've just discussed. So if S is 1, reset means Q becomes 0 and Q dash becomes 1. Is that what it is? Yes. So when C is 1 and D is 0, you get a reset state. Q is 0. Same story applies to when D is 1. If D is 1, then Q also becomes 1. Now if you notice, there's a pattern. Whatever D is there, the same value is getting into Q. So that would mean Q is nothing but D, no? Whenever C is 1, Q is taking the value of D. Whenever C is 1, Q is taking the value of D. So what does D mean? D is nothing but data. This is data latch. Whatever is the input, that will be entered into the state whenever C is 1. So D is data latch. Fine. This is the truth table. No, wait. There are two things. One is this is like the truth table. I think characteristic. Some name is there. Truth table, characteristic table. Some names are there. Just look into it. Fine. Where did XY come from? Okay, so X is nothing but D and Y is nothing but D dash. So that is how it is. X is nothing but D and Y is nothing but D dash. Or is that how it is? No, because if X is D and if D becomes 0, Y can never be... whose table is this? Okay, this is this table, no? So this is this table. This is your SR latch with control input, no? When C is 0. Yes. So this is your SR. But is there a disallowed state? No, right? So I think basically if you cut this part off and if you treat X and Y independently, this is how the table would look like. This table is nothing but if you don't have this D, if you only have X and Y directly, but won't that make it SR latch with control input, right? Hmm. Interesting. I don't know why this table is here. Let me look at it for a minute and then we'll move ahead if I don't understand why this table is here. Because if we consider this D part, then X and Y can never take the same values because X is D and Y is D bar. This can never happen. This can also never happen. And this will this is nothing but your D latch table. Fine, we'll just stick to this left side table. Right side table, I don't know why is it kept here. But for the D latch, this is the truth table. So X, in case you're wondering what X is, X means you can either put 0 there or 1 there, in case someone is still confused. Fine, so we covered cross coupled inverters, we covered SR latch, we covered SR latch with inverter, we also covered SR latch with control input, and we covered D latch. What else is there? Okay, fine. This looks fine. This slide, the same thing, nothing new. This is your SR latch, and then this part is your SR with control input, and if you add D also, this becomes your D latch. You can look at all of these three things in one place. So the higher level understanding is basically this: if you give D as 1, Q becomes 1, and if you give D as 0, Q becomes 0. All of this is assuming when C is 1. If C is 0, then whatever be the value of D, if C is 0, D can be anything, but Q will retain its previous values. So this is like reset or whatever, and this is like setting, and this is memory state. Simple. So high is basically 1 and low is basically 0. So D will only write into Q when C is high. Fine, that is all understandable. Okay, graphs are interesting. So here this is just a representation of a D latch instead of drawing this big thing every single time. So what we do is we just put it in a box, and be like D is one input, C is also one input, and you'll get Q and Q naught as outputs. So you have one big black box. Like you will also have this, I guess. You will have a dot like this and an arrow like this sometimes. So you have input as D, you have your clock or control input or enable E, you can call it whatever, and you have two outputs. One is the state and one is its complement. This is a representation, a black box representation. Now coming to the graphs, let's see how this graph. What did I tell you? I told that okay, I'll change some name. This is nothing but C, E is nothing but C, and X is nothing but D, and Z is nothing but Q, right? Okay, now maybe it will be much clear. What will be my Q? My Q will take this exact same value of D, right? So whatever D is taking, Q will take the same value. But when is it true? Whenever C is 1. So when is C 1? C is 1 in this region. So let me highlight this region. Is it same? No, it's not exact, but fine. So C is 1 in this blue color region. I'll not shade it, it will make it be. So this region, this in this blue color strip, C is equal to 1. That would mean whatever is the value of D, my Q should take the same value. So what you can notice is my Q was initially 0. Like it depends, here we are considering it is initially 0. So the moment C becomes 1, it will copy the value of D. Ditto copy paste. Copy paste. That is the property of a latch. Whenever C is high, Q will copy the value of D. In D latch at least. In a D latch, Q will copy the value of D whenever C is 1. And the moment C becomes 0, you will, what will happen? When C is 0, it will retain the previous state. So here the previous state right before C stopped being 1 is 0. So it will retain the 0 state. Let's see what will happen if I change the C. Let's see what will happen if I change the C. Let's suppose my C is this one. Let's say C went like this and then it's like this. Let's say this is my new C. This one, this is my new C. So I'll draw a new strip. So it's like this and it's like this, no? So if this is my new C, what will my new Q be? So what will Q do? Within this strip, it will ditto copy paste my D, right? So I'll draw a new Q. Let's suppose Q was initially 0. And the moment it enters this blue strip, it will copy whatever is in D. So it will copy paste. So in this blue strip, D is 1, no? So it will take the value of 1. Right? It will take the value of 1. But now the clock suddenly goes to 0, right? So what happens when the clock goes to 0? When the clock goes to 0, Q will stop copying D, that is there. But it will retain the previous value. When the clock goes to 0, Q is at state 1. So it will retain that state even after the clock goes to 0. So that is essentially what happens. Q will remain at 1 because right before the clock went to 0, Q was at 1. Now it will retain the same state because that is the property of a D latch. Once you get C equals to 0, it doesn't matter which state you're in, you will continue to retain the same state. So this graph is interesting. Fine. So I don't know why am I focusing on the graph. It looks interesting where it could be asked. I don't know. I'm not telling you it will be asked. But since it's in the slides, it's in the question. Okay, fine. Interesting. D latch we covered. This is the representation. I think I have to increase the speed. Yes, absolutely. It should cover. I'll try finishing this PPT in 30 minutes. Is that possible? Let's see. D latch is the same thing. Okay, you have nice. You have another graph. Let me just speed run through this. This is nothing but clock, no? Clock is it the same thing? Is it the same? Oh, it's the same thing. Not interesting. Fine, it's the same thing. So yes, when C is 0, it doesn't matter. If C is 0, it doesn't matter what values does D take. All that matters to this state is what is happening when C is 1. That is what matters. Nothing else matters. Only then it will do copy paste, or else nothing else will happen. And it will retain the same state as before. If it is 1, it will remain 1. If it is 0, it will remain 0. Here it becomes 0 when clock goes to 0, so it will remain 0. Fine. Symbols. So yes, so you have, this is your SR latch, your normal SR latch. You have Q and Q dash. Okay, here only you have not. So instead of giving SR, you're giving S dash and R dash. That is your S dash R dash latch. Basically your SR latch, but you're putting two inverters or whatever. Here you have Q and Q dash. And this is your D latch. If you have SR latch with control input, maybe you'll get an extra symbol like this, C. That becomes SR with control. Right? You'll get an extra input called C. Like how in a D latch you have C as an input and you get Q and Q. These are just black box representations. I mean, it's all implementation. Did we use, what did we use? We used NAND gates for SR latch, right? NOR gates. Interesting, whatever, we'll just go on. I mean, if you notice, we've already went through S dash and R dash latch. If you look at this here, we got S dash and R dash, no? So this is essentially S dash and R dash latch. If you put S and inverter, if you get what I'm saying, it's fine if you don't. Okay, some theory latches are based on combinational gates. Latches store data even after data input has been removed. Yes, we've seen memory states. SR latches operate like cross-coupled inverters with control. Yes, if you add a control input, you get SR latch with control input, right? Okay, fine. I mean, cross-coupled inverters didn't have any input. Now you have input called something called S and R. S is supposed to mean set and R is supposed to mean reset. But then in a simple SR latch, S equal to 1 resets it and R equal to 1 sets it. S equal to 1 sets it when it is SR latch with control input. To be careful, with additional gates, an SR latch can be converted into D latch. Yes, so if you give S equals to D and R equals to D dash, it becomes your D latch. D is data. So this is what I've been telling. If C is 1, Q will copy whatever D has. If C is 0, it doesn't matter what is in D. Whatever was the previous value, that will continue to be carried forward throughout time. Indefinitely, it will continue to retain the same value. Okay, this is also, so gated SR latch is essentially the same thing. Your SR latch with control input. Nothing different, nothing new in this diagram or the truth table, function table, whatever you call it. Now they are calling it enable, so it doesn't matter. Control input, enable input, clock, shouldn't matter. Okay, some notation, like in future you will find tables where you'll be writing Q plus. Q plus is nothing but the next state. Like if you give this as the input with respect to the present input, what will be with respect to the present state, what will be the next state? We'll look at some tables. Maybe there it will be more clear. More notation. Present state can be represented as Q of t. Future state can be represented as Q of t plus 1. It's all obvious, I guess. This table also we've gone through. When S is 1, it is set state. Yes, if R is 1, it is reset state. If both of them are 1, we don't know what will happen. Fine. So see, why we are saying indeterminate? Because we want Q and Q dash. Here we want Q and Q dash. We don't want the same values. That's why we are saying indeterminate. If you remember, at both the places we are getting the same values. We didn't want that. Okay, characteristic state equation. Now that you have the truth table, now we can also write functions. We can represent uh, Q as a function of S, R, and here C, I guess, enable. Is that what we're doing? Uh, okay, so truth table is here. So I guess the function table is called the characteristic table or whatever. There are two different tables. So this talks about how does the system, how does is the system, how does the latch behave? Essentially, yes. So for a given input, what will happen to the state? Fine. In the truth table, what you're supposed to do is just write all possible combinations. You can't write English sentences like this. Write the entire thing, and after you've written the truth table, you can start drawing key maps and represent Q as a function of, or you can represent Q plus as a function of S, R, and Q. Given S, R, and Q, what will be my next state? How do I get it? So let's say if I put S is 0, En is 0, R is 0. Okay, En should be 1. If En is 0, then nothing will happen. No, you'll get. If En is 0, there will be nothing happening. It will be a memory state. There will be no transition. So when En is 1, S is 0, R is 0, and let's suppose Q is 0, then what will happen? Oh my god. If S is 0, then S dash will become 1, R dash will become 1, and if 1, 1 is there, what will happen? And Q is 0 I told, so 0 will come here, feedback. 0 and 0 will give you 0, 0 not, give you 1, 1 will come here, 1 and 1 will give you 1, 1 not will give you 0. Okay. So Q is becoming 0. Q is remaining 0. So Q plus is 0. Q was initially 0. Q plus is also 0. So like this you can keep doing the truth table and find out what's going to happen. Finally you'll get this one. What is this? I mean you can do it simply also. See, whenever R becomes 1, it means you're getting reset, no? So irrespective of what is your present state, you will get 0 here. And whenever S is 1 and R is 0, that means you want to set. So irrespective of what your Q is, you will get 1 as your answer. And if both of them are 0, it means you neither want to set nor do you want to reset. So what will happen? You're doing basically nothing. If you're doing nothing, it's basically a memory state. So 0 will remain 0, 1 will remain 1. And we all know the problem in SR latch is when both of them become 1. If both of them become 1, you know what will happen, no? What will happen? Let's see, is that a problem? If S is 1, R is 1, S dash becomes 0, R dash becomes 0. 0 and 0 will give you 0, 0 not is 1. 0 and 0 will give you 0, 0 not is 1. Okay, fine, that's a problem. Q is 1, Q dash is also 1. That's a problem. We want complementary values. So if S and R both of them are 1, then that's a problem. So irrespective of what are the Q values, we do not want to first of all, we do not even want S and R to be 1. So we won't be thinking about the transition itself. It won't happen. But to fill the truth table, you can put whatever you want. It doesn't matter. Maybe don't care. Is that what happened? 110 SRQ 110. So 110. So X here X came because it doesn't matter what is the new state for these two inputs, because we don't want those inputs. But in order to fill the K map, we need to put something. So we put don't care. We don't care what is the next input. So here essentially you have X, you have X. That's why for 110 and 111. So where is 110? This is 110 and 111 is this. You have X here. Because it doesn't matter when S is 1 and R is 1, it doesn't matter what is the transition. Fine. From this K map you can get your equation. So you're trying to represent Q plus in terms of S, R and Q. You got a Boolean function from the K map. This is nothing but S because you have 1 here. And what is this? This is nothing but R dash Q, right? Because R is 0, Q is 1. So R dash Q. Q plus is nothing but S plus R dash Q. Nice. This is for your SR latch with the control input. Gated D latch, nothing much. It's essentially your D latch. I mean Q dash, Q plus will be D whenever C is 1. When C is 0, that would not be the case. And one more thing, what is the advantage of using a D latch? Because we found problems whenever S and R become equal, no? Equal to 1. So when we use a D latch, that can never happen because S is equal to D and R is equal to D dash. Both of them can't be 1 at the same time. So that is one advantage. That is what is mentioned here. The D latch, it eliminates the unstable case. Both of them can't take the same value at the same time. That is the benefit. That's the pros of using a D latch. You have your own truth table for a gated D latch. Gated D latch is essentially a D latch, nothing different. So what is G here? Is G... Okay, they're calling it G now instead of C. Here your G is nothing but your C. So shouldn't matter. G is nothing but your D. G, they're writing it G maybe because, okay, they told let's take clock as G. Fine, their wish. First enable clock control input. Now G. G for gate, I guess. We all know that whenever the clock is 0, it doesn't matter what is the value of D. Whenever clock is 0, the state will not change. 0 will remain 0, 1 will remain 1. You can easily fill up the truth table. You don't even have to go through all combinations. And when G is 1, now we have to see whether set is happening or reset is happening. I mean, in a D latch, it is simple. Whenever clock is 1, Q will, the next state will copy whatever D has. So if D has 0, the next state will become 0. So if D has 0, the next state will become 0. It doesn't matter what is the present state. It will directly copy whatever is the value in D. Since the clock is 1, whatever D has, that will go on to the next state. Done. You filled the truth table. You didn't even have to go through all you didn't have to go through this entire thing and check one by one what is the final answer. As long as you remember what's happening fundamentally, you should be able to fill the truth table. Now that you have the truth table, now it's time to write. Okay, so here you have two tables, no? So this is the truth table. I think this is called the transition table or state transition table, I think in the tutorial it was there, state diagram, state transition table or whatever. I think this is considering only which values? These values, I think, right? Yes, because it doesn't matter when clock is 0. This is considering only when clock is 1. So this table is for when clock is 1. That is only when you have transitions happening. When clock is 0, there is no transition happening, so it won't make sense to add it in a transition table. Okay, fine. So from truth table we will fill up this K map, and from K map you can get your equation representing the next state in terms of clock, the present state, as well as D. Here clock is given as G, present state is Q, D is the data. So you can see it for yourself. Whenever G is 1, it will directly copy D, and this becomes 0. And whenever G is 0, this goes off and this becomes 1. What remains is Q. So essentially, whenever clock is 0, you will retain the same state. That is the meaning. Equations you don't have to by heart. If you know the procedure, you can directly write the truth table and then draw K-maps. Or you can directly remember, like D latch, what happens in a D latch? When clock is 1, it will copy. When clock is 1, it will copy D. When clock is 0, it will retain the same state. Fine, that is D latch. Think we'll be moving on to flip flops. Basic latch. Latch is fine. Theory, basic latch, gated latch. I think they're calling it a gated latch when you have a clock as an input. That's it, no? That's it, I guess. So basic latch is something like that cross-coupled inverter, I guess. Flip-flop. Flip-flop is a new thing. We will look into it. Flip-flop. So flip-flop will make transitions when the clock changes. So we look into it. What does it mean? So you understand triggering, right? So latches will trigger with respect to the level. So let's say the clock looks like this. These are called levels. You have level 1, level 0. So when I say triggers on levels, it will basically look at what's happening in the level. So whenever it's level 1, I will do something. If it's level 0, I won't do anything. That is level triggering. But what do I mean by edge triggering? There is something called edge triggering. Edge triggering is of two kinds. You have 0 to 1, no? That's a positive edge. You have 1 to 0. That's a negative edge. So if something gets triggered by this rise and fall, so basically only here, it doesn't matter whether the level is 0 or 1. What matters is, are you moving from 0 to 1 or are you falling from 1 to 0? Two things matter. So it depends on the type. So this is positive edge because it's going from bottom to top. This is negative edge going from top to bottom. We'll look into where this is being applied. So you have, so latches basically look at levels. We've looked at the graph, no? I told whenever clock is 1, in a D latch, Q will always copy D. It will always copy the value in D. So it's looking at the level. But flip-flops are different. We will look at an example, then you'll understand. Flip-flops will depend on the edge. It will get triggered by either a positive edge or a negative edge. Maybe an example should help you. And so why do we need flip-flops? Apparently they've given a reason. It's difficult to precisely time when to store data. I don't have an example as to explain why this is true or whatever. But apparently latches are difficult to work with. Flip-flops are better. You can precisely time when to store data, apparently. Fine. So latches and flip-flops, currently what is the difference? Latches are level triggered, flip-flops are edge triggered, and edge triggering is of two kinds: positive edge triggering and negative edge triggering. Fine, okay, they've given differences. So level sensitive, edge sensitive. Basically, if clock is like this, latch will look for levels. Is it at level 1? Is it at level 2? This is what latches look at. But what do flip-flops look at? Flip-flops will look at the edges. What is happening at the edge? Is it going from top to bottom or bottom to top? If it's only looking from bottom to top, it's a positive edge triggered. So 0 to 1. Where is 0 to 1 happening? That is positive edge triggered. Where is 1 to 0 happening? That is negative edge triggered. So flip-flops will make transitions whenever these edges are encountered. That is how latches and flip-flops are different. How do I build a flip-flop? They told you can use latches. We will see how to use latches to build a flip-flop. So we look at our first example. There is a black box and it is supposedly a positive edge triggered flip-flop. They've given the truth table. We look at what does it mean. You can look at an arrow in the clock, right? If the arrow is upwards, it means it's a positive edge triggered flip-flop. So it means whenever the clock is going up, that is when the transition happens. What kind of transition? Let's see. I mean, it's essentially your D latch. Same thing. Whenever D is 0, Q will be 0. Whenever D is 1, Q will be 1. And if clock is not detecting positive edge, which means nothing is happening, clock is 0, then it doesn't matter what D is, it will retain the previous states. So everything is same. Everything is similar to D latch, but this becomes a D flip flop because this transition will happen not because of C equal to 1, but the transition will happen because whenever C moves from 0 to 1, that is when the transition happens. So it is okay. I think, is there a graph here? Yes. So whenever this trigger happens, whenever C moves from 0 to 1, in that short span of time, the transition happens. So let's say this is the clock, and let's say D is let's say this is D, and let's look at what will happen to a Q in a D latch, and let's look at what will happen to Q in a D flip-flop. Okay, what will happen in D latch? D latch, what it will do? It will simply copy whatever is there in D whenever C is 1. C is 1 in this range, in this strip. So what will D latch do? It will simply copy whatever is there. No? Let's say initially Q is at 0. So it will start at 0. No? Q is at 0. It is starting at 0. And it will copy whatever is in D. D looks like this. When clock is 1, D looks like that in this strip. And now suddenly clock becomes 0. Then what will D latch do? It will retain the previous value. So previously it was at 1 right before the clock goes to 0. So it will retain this graph. So this is how a D latch will look like. Let's see if a D flip-flop will behave differently. Let's hope that it behaves differently so that you can look at the difference. If it doesn't behave differently, then I'll have to think of another example. Maybe we'll see in the following slides. But let's see how does a D flip-flop behave. Let's say D flip-flop also starts at Q equal to 0. When does the Q flip-flop get triggered? It triggers. Okay, let's say this is a positive edge triggered. So I'll write positive somewhere. Positive. Fine. So positive edge triggered means, let me remove the strips here. These strips are no longer necessary. Because what does a flip-flop look at? It will search for edges. It will not look at levels. So where is a positive edge here? Positive edge is over here. Only one positive edge. We will not look at negative edge because I told you this is positive edge triggered flip-flop. A D type. So positive edge is here, no? So let's see what will happen to this D latch. Let's assume it's at 0, no? Let's assume it's at 0. Now suddenly there is a trigger. There is a trigger at the positive edge. So when there is a trigger at the positive edge, what are you supposed to do? Same thing. Now, after it gets triggered, you follow the truth table. What does the truth table say? If D is 0, Q must also be 0. So what you're supposed to do? Here you set Q value to 0. So here it will be at 0. At that instant, you set Q value to 0. Now the triggering event is over. Now you have to do nothing. After the trigger is over, you set your Q value to 0 and then you retain the same value. You retain the same value. You're not going to follow what D is doing. Only at that particular instant when C goes from 0 to 1, you change the value of Q. Here, unfortunately, D is still at 0 when the event is triggered. So Q will copy the value and store 0. Now what will happen? There is no more trigger. It's just one small edge. At that instant, Q became 0. So it will retain the same value and remain 0 for the rest of its lifetime. Okay, this example is nice because now you can see the difference between a D latch and a D type positive edge triggered flip flop. So D latch will simply copy what D has whenever C is 1. But flip flops are different. They will look at edges. Is it going from 0 to 1 or is it going from 1 to 0? Here this is a positive edge triggered flip flop. So it is going to look for 0 to 1 transition. So here it is happening. At that instant, what is the value of D? It is 0. So it will set Q to 0 and it will continue to retain the same value. There is no change. Let's see what will happen if you have negative edge triggered flip flop. Is there place here? Negative edge triggered flip. Okay, there's some place here. Negative edge triggered flip flop. I'll draw here only. This is a D type negative edge triggered flip flop. Let's say it also starts from 0. First, you have to search where is your negative edge. Your negative edge is. Oh my god. Your negative edge is here, no? 1 to 0. That is your negative edge. So let me draw that. So this is your negative edge. So until that event is triggered, your flip flop will continue to have 0 because it is peacefully living its life. Now that you've triggered negative edge, it will copy whatever value D has. If you look at this intersection, D is currently at 1. When the negative edge was triggered, D was at 1. So now you will have to, and according to the truth table, what is there? Here it is positive edge. If it's negative edge, you simply have a down arrow. You'll have a negative arrow. So what does it mean in a D latch? Whenever the event is triggered, you copy the value that D has. Here D has 1, so you set Q to 1. So Q goes to 1 here. Now the event, it got triggered, over. The work is done. So after the event is triggered, what do? You do nothing. You retain the same value. So now that you've set Q to 1, you will retain the same value. It goes on. So flip-flops, they're different from latches because flip-flops will copy D only for that particular instant, but latches will copy D for their entire level. That is how they're different. So here you can see the difference between the D latch, the D positive flip-flop as well as D negative flip-flop. Here you got 3 different graphs. I love this example because it shows you the difference between all these three devices. Nice. So this graph is nice. So this is just a D latch. You have more D latch, D flip flop, whatever. You have more interesting flip flops. Okay, fine. This graph you can think about it later. I will move ahead. The graph is interesting. Like if you understand the truth table, then you should be able to do this. Should be fine. Okay, question. How to implement flip flop? Flip flop, we've seen it as a black box. We don't know what is inside. We will see what is inside now. So here I will be using 2 latches to implement a flip flop. Okay, which flip flop is this? This is a negative edge triggered flip flop. Why negative edge? You will understand. Let's see. So here you have 2 latches. One is called the master. The other is called the slave. And we know for a D latch you have D as an input. You have clock, enable, call it whatever you want. And here is your Q. Okay, let's see if clock is 0. Let's say clock is 0. So let's say clock is 0 like this. Clock is 0. Nothing is happening. If clock is 0, then what will happen? Here you will get 0. Here you will get 1 because inverter is here, no? Let's see what will happen. And here D is there. Okay, so if you look at this particular latch, if you look at the master latch, what does it mean when clock is 0? If clock is 0, it means you're retaining the state. So Q will not change. Irrespective of the values of D, Q will not change. So the output of this master latch is simply Q. Like whatever is its previous state. So I'm assuming it has state Q or Q naught. Let's say Q naught. So the previous state is Q naught. So it will simply give Q naught. No change when clock is 0. Now let's look at the slave latch. What is happening in the slave latch? Clock turns out to be 1. And what does it mean when clock is 1? When clock is 1, what will the D latch do? It will copy whatever is the value in D. In D, the value that you have is, you just received Q naught. So you'll copy this value and throw it out of this. You'll get Q naught again. So what just happened? Nothing happened. So nothing exactly happened now. We've just filled some values. Now let's see when clock, so nothing happens here when clock is 0. Clock is 0, clock is 0, clock is 0, clock is 0, clock is 0. Now let's say we're entering this region. Clock goes to 1, stays 1 for a while and goes to 0. Let's see what happens now. So let me say this is point A and this is point B. At point A, clock is entering 1, right? So let me change the value. So clock which was 0 becomes 1. Now let's change everything. So this becomes 1, this becomes 0, no? Yes. So let's look at the master latch. When clock is 1, what does it mean? When clock is 1, what does it mean? You copy the value of D, right? So let's say D is D only. So whatever is in D will come here. So this initial state will get overwritten by D. So output is D. Initially there was Q naught, but now it's gone because clock became 1. So D will take over. D will become the output. Whatever is the input will become the output. This state will get overwritten. So you get D here. Fine. That is the master latch. Let's look at the slave latch. What is happening in the slave latch? Slave latch turns out clock became 0, no? So what does it mean? When clock becomes 0 in a latch, it means irrespective of the values of D, you will retain the same state. So here input we are getting D, but that will not affect the output because clock is 0. So whatever was its original state, which was Q naught, it will remain Q naught. So output is still Q naught here. So if you notice, all this time when clock was 0, output was Q naught. Even after clock became 1, output is still Q naught. It's not changing. Notice. That is why this is a negative edge triggered, a negative edge triggered flip-flop. There is a positive edge here, but it's not responding. Q naught is still Q naught. So you can see what is happening here. Now I will show you what will happen at point B. I will tell you what will happen now only. At point B, Q naught is going to change. And that is what makes it a negative edge triggered flip-flop. We will see. Now at point B, what will happen is clock is falling from 0 to 1, 1 to 0. My bad. Clock is falling from 1 to 0. So let me make that change here. Clock which is currently at 1 becomes 0. So if clock becomes 0, what will happen? My master will get 0 and my slave will get 1. Now let's look at the changes here. Now what does it mean when the master D latch gets clock as 0? It means you're going to retain the previous state. And if you're retaining the previous state, good for us. So previously it was D, it will continue to remain D. My Q naught became D and D will remain D because now clock is 0. Fine, this is simple. Master latch is simple. Now slave latch. What is happening at slave latch? My current state is Q naught, but my clock became 1. So what does it mean when clock is 1 for a latch? Your Q will copy the D value. So your D input is D here. I'm using the same variable, but it's fine. You can understand. So this D is going to change the state of the slave latch. So Q naught is going to get overwritten and it will become D. Why? Because clock in D latch became 1. So whatever is the input will be thrown into the output. So it is only after the negative edge does the Q become D. Now you can see, if you look at this on a higher level, Q naught remained Q naught until a negative edge came into the picture. After the negative edge came into the picture, you were able to see this change called D. So this is a negative edge triggered flip flop. You can implement it using two latches, master latch, slave latch. You can look at this diagram. This is simple. This is done. Nothing much to be said. Interesting things happening around. So how do I make a positive edge triggered? Simple. What you do is just you can put the inverter here and remove this inverter. Everything else will be same. Then it will become a positive edge triggered. You can do the you can do the workings on your own. So it's simple. Fine. So this is your master slave D flip flop implementing flip flop using master slave latches. Okay, now you have a black box. This was the internal workings. Now I have a symbol. I can represent my flip flop using this black box. You have an input D, you have an output Q, and then you have a clock. This is your D flip flop. Okay, I forgot. These were there are some names. There are some names. Whenever clock and wait, which flip flop is this again? Let me see. Which flip flop is this? Positive edge. Okay, this is positive edge triggered flip flop. Okay, fine. So positive edge means here you should have an inverter to the master, and slave should not have an inverter. You should have an inverter to the master, and slave should not have an inverter. Then it will become a positive edge triggered flip flop. So if you notice, let's consider the positive edge triggered flip flop. When clock is 0, my master will get 1. When clock is 0, in a positive edge triggered flip flop, my master will get 1. So if the master gets clock as 1, what does it mean? You're going to change the value, right? Because whenever clock is 1, my D is going to overwrite Q. My Q will copy D. So you call that state as transparent. You're calling that state as transparent because whatever is the input is becoming the output. So in a positive flip flop, when the clock is 0, my master latch gets a clock of 1 because there is an inverter. And if clock is 1, you're copying the value of D into Q. So that's transparent. And simultaneously, my slave will get a clock of 0. And a clock of 0 in a latch means you're not going to do anything. It's a memory state. You're going to hold on to the same state. So it's called the hold state, the hold mode. Transparent mode, hold mode. And if now this is a positive edge trigger, right? Whenever there is a trigger, when there is a positive edge, only for that particular instant, master. I mean, whenever clock is 1 also, I can simply say whenever the clock is 1, my master will go into hold and slave will go into transparent mode. Simple. You can see. Whenever clock is 1, my master will get what? Here inverter is there. No? So master will get clock 0. So master will enter hold mode. And here there is no inverter. So clock becoming 1 means slave will get clock 1. So that would mean clock enters transparent mode. So that is what is here. So nice, some terminology here. Some graphs are here. You can try going through them yourself. Or you want me to go through them? Okay, let's see. Clock is there, it's going up, going down, going up, going down. So these are positive edges. These are the events that are going to trigger your transitions. And you have an interesting looking D. It's going up, down, up, down, up, down. So let's see what's going to happen. Let's follow what will happen with this. This is one example. They've combined two examples in the same space. Let's look at what is going to happen when this is your D. So what is Q master? Q master is nothing but this output of the master, no? So what is master going to do? In a positive edge trigger, here we can see, no? When clock is 1, master is going to hold. When clock is 1, master is going to hold. So let's say master is going to hold. So what is oh my god, so many lines here. Let me see what's happening. Just a minute. Okay, so let's follow some line. Let's say we're following this line. Okay, so let's say Q is, wait, I have to see which line is which line. Let's say D is going to 1. Okay, fine. Let's follow something. So you have a positive trigger at the first step only, no? So what would that mean? My Q master has to get triggered. Like the flip flop has to get triggered. But what is happening to Q master when this transition is happening? Master is holding, so it's holding on to the previous value. But what is the previous value here? Okay, let's say the previous value is 1 and it's holding on to 1. Clock is 0 means it has to copy what D is doing. Okay, fine. So when clock is 0, master is going to get 1, no? In a positive. So when clock is 0, master will get 1. So if master is getting 1, whatever is in D will enter Q master. So here D is rising when clock was 0 previously. Clock was previously 0 and D is rising. If D is rising, then that would mean Q master was also rising, right? Yes, because when clock is 0, Q master's clock was 1 because there is an inverter. When the clock is 0, Q master's clock is 1. So that would mean it has been copying D. So that is the reason. When D is increasing, Q master is also increasing. And suddenly when clock became 1, Q master's clock will become 0. And when Q master's clock becomes 0, what does it mean? That latch is going to hold on to the state that it currently has, because when clock is 0, it's a memory state, no change. So it will continue to hold on to that state. And now suddenly clock becomes 0. When clock becomes 0, master's clock becomes 1 because there is an inverter. And if master's clock becomes 1, it will copy whatever value D has. So D is now D, if you look at it, it's going down, up. It's going like this. Now suddenly clock becomes 1. If clock becomes 1, master's clock becomes 0. Because I'll show you again. In a positive edge triggered flip flop, master's clock is the opposite of the clock. Like if clock is 0, master's clock is 1 because there's an inverter. So where was I? So clock suddenly became 1. So master's clock becomes 0. If master's clock becomes 0, you retain the same value. And now suddenly clock is becoming 0. When clock becomes 0, master's clock becomes 1. And when it becomes 1, you copy whatever D value is there. D is going down and up. So you go down, up, down, up. Now suddenly clock becomes 1. When clock becomes 1, master's clock becomes 0. If master's clock becomes 0, you retain the same value. So this is the story of QM. This is the story of what happens here. Here in this between what is happening. That is the story here. We are following what is happening to the output of the master latch in a positive edge triggered D flip flop. Fine. That is QM. What is Q here? Q is the final output. The output of the slave. The final output. Let's see what is happening to the slave. When slave's clock and the original clock, both of them have the same thing, so it should not cause a problem, I guess. And if you notice, the slave latch's input is the output of the master latch. So our new D is nothing but QM. QM is nothing but the D of the slave latch. So whenever clock is 1 for Q, it will follow QM. And whenever clock is 0, it will retain the value. So let's see what is happening. which line is this again? So initially clock was 0, so Q will do nothing, right? Q should be retaining its old value. Okay, let's say let's say it starts from here. It doesn't make sense though. Okay, I'll start from here. I'll ignore the initial part. Let's say it starts from 1. And when here clock is 1, no? So when clock is 1, what is going to happen? It is going to copy whatever is there in its input. Its input is QM. So it will keep copying QM. So after copying until QM, what is it going to do? Suddenly it realizes clock is 0. And when clock is 0, what is my slave latch going to do? Nothing. It's going to retain its previous value. So it will continue to retain its previous value. And now suddenly clock goes to 1. When clock goes to 1, now this is interesting. Now what is happening? Even I don't know. When clock goes to 1, it's supposed to copy whatever is happening in QM. But it looks like it's not falling at all. Right? It doesn't look like it's falling. If clock is like this, you have positive edges like this. And when you have Q, when you have something like this, go like this, like this, like this, then what is going to happen? Let's say you're starting at 1. This is your event. This is your event. This is your event. Whenever this event is happening, you are at 1 only, no? It looks like it's not going to fall at all. Then I don't see why is there I don't understand why is there a fall here. Why is it falling? You get my point, no? So maybe you can think about it. We'll come to this graph later. But until here, I think it's supposed to be clear. It's just too many lines kept in one place, so I don't think it is clear enough as to which line is for which one. But you get the point, no? Whenever there is a positive edge trigger, that is when the Q changes. And if it's not changing only, then it will remain at 1. Nothing is going to happen. Fine. We will look at this later, but I think I've given much clarity. You can think about this yourselves. D flip-flop, the same thing again and again. This is positive. So this is the positive edge triggered flip-flop. Clocked, whatever, everything is same. You have a clock, that's it. You have a periodic synchronous clock. Because look at this periodic. Okay, you have one more example here, no? Let's look at this. You have positive edges here, here, here. Whenever you have positive edge, you simply copy the D value. At this edge, D is... so here Q is starting at 1. So let's suppose it starts at 1. At the first positive edge, it's at 0. So you go to 0, set your Q to 0 and live over there until the next trigger comes. Here the next trigger, it says D is at 1. So set your Q to 1 and go there and sit there until the next trigger happens. At the next trigger, you have D at 0. So you set your Q to 0 and still just sit there until the next trigger happens. The next trigger is at 1, so you go to 1 and sit there. Here, see, the next trigger happens, it's still at 1, so it will remain at 1. So that was a problem that was happening before. It will remain at 1. Here, the next trigger happens, you go down to 0 and then you still sit there. The next trigger happens, it's still at 0, so you will remain sitting at 0. So this is how flip-flops work. flip-flops will simply change whenever there is an edge trigger. Latches are different because they'll copy the same thing. Ditto copy paste will happen, whatever is in that interval. Uh, okay, so you have some representations. They're just representations, nothing much to be told here. Example. What example is this? Okay, so they just kept all these three things in the same circuit. Nothing different here. There's nothing in this. It's just their timing diagram. Okay. You just have to look at the symbols. Then this there. There's nothing. You can look at the graphs. Graphs are interesting. We looked at a lot of graphs. You can look at graphs yourself. JK flip flop. New flip flop. How is it different? We had our nice little D flip flop. Where is our D flip flop? This is our D flip flop. You do some magic, it becomes JK flip flop. What is that magic? You have your new inputs J and K. For some reason, there is an inverter here. You put an AND gate. You put an OR gate, and then you put feedback also. You take Q dash and give it to J. You take Q and give it to this AND gate. Nice. This is the internal workings of a JK flip flop. This is the black box. Truth table. So this is a flip flop. You'll have to look at triggers. That's why you have arrows here. 0 arrow means I think it goes from 0 to 1. 1 arrow means my bad. This is K values. Arrow means it's going from 0 to 1. So positive edge triggered flip flop. I don't think I'll be going through every single detail as to why everything is happening here. We've looked at the D latch. So same logic you apply here, you'll understand why we got this truth table. I mean, it's simple. You can put J0, K0 and see what is happening. So we'll look at the higher level understanding. So J equals to 1 means you're setting. So when J is 1 and K is 0, are you setting it? Are you sure? Yes. So Q becomes 1. Is that the meaning? Yes. So J equals to 1 and K equals to 0 means you're setting it because your Q becomes 1 and K resets. K resets means when K becomes 1 and J is 0, your state will become 0. It is similar to that SR latch, no? When S is 1, you're getting set. SR latch with control input. When S is 1, you're getting set. When R is 1, you're getting reset. Here also same. When J is 1, you're getting set. When K is 1, you're getting reset. And if both are 1, and when both are 1, what will happen? You'll get toggle. What does toggle mean? Memory state is different. When J and K are 0, you're getting memory state. And what does memory state mean? You are going to retain the same previous values. But what does toggle mean? Toggle means whatever is your current input state, you invert it. So if you had Q0 initially, it becomes Q0 dash. For example, if you had 0 initially, it becomes 1. If you had 1 initially, it becomes 0. It doesn't matter. You just invert your initial state. That is what toggle means. So you have memory state, you have reset state, you have set state, you have a toggle state. So this is a new thing. That's why we have a JK flip-flop. This is a positive edge triggered JK flip-flop. To make it a negative edge, I will see. I think they'll give us. So clocked, essentially you have a clock. Here also you have a clock now. Do you have a clock? Yeah, you have a clock. The same thing. It's the same thing. Mm. Graphs also. We looked at graphs, so you should be able to tell now. So positive edge means wherever there is a positive edge, that's where the transition happens. You change the Q value. But here you don't have D, you have J as well as K. You'll have to look at the truth table. Like if J and K are 0, then memory state. Here you're not copying anything. You have to understand. If J and K and 0, you're getting memory no change. If J is 1, it means set state. If K is 1, it means reset state. If J is 1 and K is 1, if both of them are 1, you get a toggle state. For example, here J is 0 and K is 1. It means reset state. No, K is 1 means reset state. So whatever was your... oh, they didn't give? Oh, they've given. So if you start at 1, because of J and K value and positive edge trigger, you go to 0. Because K equals to 1 means reset state. Here K is 1, J is 1. So what does it mean? It means toggle state. What does toggle state mean? Whatever is your initial state, you invert it. 0 becomes 1, 1 becomes 0. And so on. You can do the graph by yourself. How did we obtain the truth table? You can put values here and check. That's doable. There's nothing for me to tell in that. But the graphs are... you'll have to know how to use them. So you'll have to keep some things in mind. Like for JK flip-flop, 0, 0 means memory state. If J is 1, it means set state. If K is 1, it means... If K is 1, it means reset state. If both of them are 1, it's toggle state. Negative edge, once look into it. How to make JK negative edge triggered. I didn't look into it. I'll try looking into it. Okay, D flip-flop, JK flip-flop, now T flip-flop. T flip-flop is a new thing. If there's nothing much in a T flip-flop, it's similar to D, I think. The same input you're giving to J and K. Like J equals to K equals to T. Is that how it is? Yes. In a JK flip-flop, if you give J equals to T and K equals to T, basically if you give the same input to J and K, you'll get a T flip-flop. So what would that mean? In JK flip-flop, it means input is either 0, 0 or 1, 1. We'll look into it. We'll look into the truth table of a T flip-flop. You have other representations. How to write a T flip-flop using a D flip-flop. It's just another representation. Because from D flip-flop only we got JK flip-flop. From D flip-flop we got JK flip-flop. And you're putting J and K as the same. If you put J and K as T, you're getting T flip-flop. So after some simplifications, probably you're getting that second representation. This representation you're getting. After some simplification, probably you're getting this one. And this is your black box. You have an input T, you have clock, and then you have Q and Q dash as outputs. So truth table is simple here because T is either 0 or 1. And this is positive edge triggered. Once look at how to represent negative edge triggered somewhere. I think somewhere you'll get a circle or whatever. Once look into it. But this is positive edge triggered. So positive edge triggered means whenever clock goes from 0 to 1, you have a transition. How did we get the truth table? You can verify. Like if T is 0, it means J and K both are 0. And in JK flip-flop, if J and K both of them are 0, it's a memory state. So Q0 remains Q0, which essentially means Q0 dash remains Q0 dash. But when T is 1, it means J equals to K equals to 1. And in JK flip-flop, if both of them are 1, you get a toggle state. So toggle state means you change the values. You invert the values. So if you have Q0, it becomes Q0 dash. And Q0 dash becomes Q0 dash dash, which is nothing but Q0. So you toggle your states. Simple. So if T is 0, you retain. If T is 1, you toggle. There is no set reset here. It's just memory state, toggle state. That is your T flip-flop. Okay, you have summaries. JK flip flops. Yes, so this it's good to keep this in mind. For a JK flip flop, if you have 0 0, then it's a memory state, no change. If K is 1, you're resetting it. What do I mean by reset? Reset means your state is becoming 0. It doesn't matter if Q is 1 or 0. If reset, it means this becomes 0 or this becomes 0. It doesn't matter. It doesn't matter what is the initial value. Reset means your state becomes 0. Set means your state becomes 1. So when does it happen? When J is 1. If both of them are 1, you have a toggle. Toggle means you're just going to invert your current state. So initially it was Q, it becomes Q dash now. So if you had 1, 1 will become 0. If you had 0, it will become 1. D flip flop. D flip flop is basically whenever clock is 1, like whenever clock is 1, my Q will copy whatever is in D. So D will make Q 0 if D is 0, and Q will make D will make Q 1 when D is 1. So reset set fine when clock is 1. If clock is 0, then there is no change, that's a memory state. Even in JK, what happens if clock is 0? Did they mention that? Okay, fine, it's a flip flop, no? It doesn't matter. What matters is the triggers. My bad. What matters is the triggers. If there is no trigger, it will not do anything. It will simply retain. So it's a memory state. If there is no positive edge trigger, then it will be memory state. No change. It's a flip flop, no? It's triggered by edges. I don't have to mention clock again and again here. Like these changes happen when clock is whenever the trigger happens, assuming they are positive edge. If they're positive edge triggered, this is what happens. If they're negative edge triggered, then so transition table is same. All that matters is when is it getting triggered? Is it positive edge trigger or is it negative edge triggered? Or else everything else is same. I guess that's why they didn't mention anything. T flip flop. T0 means no change, memory state. T1 means you have toggle state. Okay, asynchronous inputs. I'll give you an example of a synchronous input. Clock is a synchronous input. I guess J and K are synchronous. Yes, they're synchronized with clock. So J and K are synchronous because they're synchronized with clock. Synchronous in the sense they're not coming randomly. They're coming like periodically or whatever. You can think of them that way. It's like a can I say sine wave? It's like periodic. You can think of a period, like toing, or it goes like this. It's not abrupt or whatever. You understand, I guess. I don't have to tell much. But asynchronous inputs is it's not periodic. It's abrupt. Abrupt. You can control. You can send a signal in between and change how does the flip flop work. So those kinds of inputs are called asynchronous. Let's look at some examples if there are any. Like they won't depend on the clock. It depends on us. So this is what I was talking about. You have clear and preset. So it doesn't depend on the clock. We just, let's say something goes wrong. So we will come in between and give this as input. So it doesn't depend on the clock. It happens randomly. Let's say today I decide, let me clear whatever is in this flip flop. So I'll press this button and it is going to clear everything in this flip flop. Let's see what exactly is happening. So clear means I think it's going to set everything to 0, I suppose. Right? Let's see. Preset to 1, clear 1. Clocked operation. Q will respond. Okay. Let's look at preset 0 and clear 1. So it means we are not presetting but we are clearing. Is that what it means? Yes. So we are clearing. I think when we are clearing it, we are setting Q to 1. Counterintuitive. No, I thought clearing we'll put it to 0, but we are not doing that. So clearing turns out to be setting Q to 1, irrespective of what is the clock value. So we we are asynchronously interfering into this working of a flip-flop. So irrespective of what is clock value, whatever, whenever clear is 1, Q is 1. Like clock is nicely happening, but suddenly there is a signal in between and it's saying clear. When that clear signal comes from this input, it makes Q as 1. Suddenly, at that instant, Q will become 1 when this signal is given. It could be anywhere. We don't know. It could be here, it could be here. We wouldn't know. But at one instant, this signal will come and the clear signal will make Q equals to 1. Same with preset. What will preset do? When preset is 1 and clear is 0, preset is like reset, I guess. So it's going to set the Q to 0, irrespective of what is the clock value. And the other inputs, I guess. So asynchronous inputs. So basically extra inputs that are interfering with the normal business of this flip-flop. And if both of them are 1, they told that it's going to do its normal business. Whatever it was supposed to do, it will keep doing. It's like preset, you want to do preset, you want to do clear also. So both of them will clash and essentially nothing will happen. I guess that is one kind of thinking. You can think of it that way. So when preset and clear are 1, nothing happens. But when clear is 1 and preset is 0, it will make Q equals to 1 according to this table. And preset will make Q equals to 0. It's going to interfere. So the graph will change if in case they ask, if in case they put preset or clear in the graph, which I don't think they will. That's too much. So both of them are 0 means okay, fine, they're not used. Because you're already assigning 1 1 as normal usage. What will you put 0 0 as? They're not used. Fine. Let's see if they're okay. Oh, there is a graph. There is a graph. Okay. Okay, there is a graph. Interesting. Thought they won't give, but okay, fine. So we have clocks here, which what kind of a flip-flop is this? It is a JK flip-flop. I see J and K. I'm assuming it is a positive. Is it a positive edge triggered? How will I know? It looks like it's a negative edge triggered, no? Because I see all these lines as the negative clock. Okay, look at this. Clock negative. You have clock negative over there. I'll show you JK flip-flops diagram. See, this is your JK flip-flop. Positive edge triggered JK flip-flop. If you want to make it negative edge triggered JK flip-flop, you have to negate the clock input. For this black box model, I'm not talking about master slave latch. I'm telling you how to represent a negative flip-flop. So if there is a negation, it means it's a negative edge triggered flip-flop. So that is what is happening in that graph. If you look at the diagram, here I'm getting clock bar. So I'm getting an inverted clock, right? Hopefully, am I right? Or am I wrong? I don't know. I think I should. I think that is one explanation, hopefully, because I see bar here, I also see a circle here, so it doesn't make sense. But anyways, you can look into it, but this is established. Apparently, this is a negative edge triggered JK flip-flop. And here J and K is 1 throughout the entire graph. So let's see what will happen. When J and K is 1, what does it mean in a normal JK flip-flop? When J and K is 1, you're toggling it, right? When J and K is 1, what are you doing? Toggle. Yes, when J and K is 1, you're toggling it. So let's say Q starts at 1. And we know that preset equal to clear equal to 1 means normal usage. Nothing wrong is happening. Whatever happens will happen accordingly, according to the clock. So at this dotted line, you have your first negative edge. So your Q is going to get triggered. J and K is always 1, so it means toggle. So you now toggle. 1 becomes 0 because toggle. You invert your state. And then you're going to live peacefully. You're going to live peacefully. And then someone decided, let me preset. Let me send preset to 0. If you send preset to 0, your clock is, your clear is still at 1. So it means at this instant of time you have clear. And when you have clear, your Q will be sent to 1, irrespective of the clock. So your Q, which was nicely living at 0, will directly be sent to 1 because preset was set to 0 and clear is currently at 1. So preset 0, clear 1 means your Q will be set to 1 without any, it won't wait for the clock. Directly it will be set to 1. Okay, this is done. It will live for a while peacefully. And here preset went to 1. Will something wrong happen? No, nothing is going to change because when preset and clear are at 1, no change is going to happen. It's going to continue the same process according to the clock. Clocked operation means they will respond naturally, normally. No instant changes will happen. Normally, however, J and K flip-flop will work. That's how they will continue to function. And now you have your second negative edge in the clock. So your Q will get triggered. J and K, as usual, here it's given, it's at 1. So you will toggle. So currently you're at 1. So you will toggle from 1 to 0. And you will continue to retain that state peacefully until the next trigger. Here you have another negative edge trigger. And if you have a negative edge trigger, your negative edge triggered JK flip flop will react. How will it react? It sees J and K is 1. JK1 means toggle. Toggle means if you're at 0, you go to 1. If you're at 1, you go to 0. Here you're at 0, you go to 1. And you live peacefully for a while, like this. And now someone decides, let me send clear to 0. Let me send clear to 0. But now preset is at 1. Is at 1. So if clear is at 0 and preset is at 1, what does it mean? It means preset. And preset means you send Q to 0. Irrespective of the clock, you send Q to 0. So here suddenly Q goes to 0 because preset is at 1 and clear is at 0. And then you continue to live peacefully. And then there is a next negative edge trigger. What happens? Negative edge, so you'll have to respond. No? J and K is 1. You will toggle. Right? But here we are not toggling. Why is that the case? Okay, so here clear is still at 0, no? So until clear is at 0, nothing is going to happen because preset is at 1, clear is at 0. That would mean Q has to remain at 0. Whenever preset is at 0 and clear is at 1, Q has to remain at 0 irrespective of the clock. That is what is given in this table. When preset is at 0 and clear is at 1, Q has to remain at 1 irrespective of the clock. So despite there being a trigger and despite the flip-flop wanting to toggle from 0 to 1, it will not happen because of this clear and preset. This toggle would have happened had preset and clear been 1, because if both of them were 1, then you would have normal operation of the JK flip-flop. So this is an important thing if this graph comes miraculously or whatever, I don't know. So there is no toggle here, no toggle, because this thing is still here. My clear is still at 0, my preset is at 1. Fine. Now fortunately my clear goes back to 1. Now preset and clear, both of them are 1 for the rest of the graph, so I will not be bothered by it. Now I can continue with my normal functioning of the JK flip-flop, and the next event trigger happens here. Now I can peacefully toggle from 0 to 1. JK is 1. If J and K are 1, you toggle. You peacefully toggle from 0 to 1 because my preset and clear are not causing any problems because both of them are at 1. Preset and clear won't be 0 at the same time because of this table. They are not used. So you'll have to see if preset and clear both are at 1, normal operation of JK flip-flop. But if preset is at 0, it means Q has to remain at 1. And if clear is at 0, it means Q has to remain at 0, regardless of clock. So that is what this table means. This table is used, whatever is in this table, I used to understand what this graph is trying to tell me. Oh my god. Did I miss something very important? Do you see a bar on the top? Do you see a bar on the top? Does it mean it's clear dash and preset dash? Now it makes sense, no? Because if clear is 1, I want my Q to become 0. But here when clear is 1, it shows Q is 1. So let me confirm. I am thinking this is... But there is a dash everywhere. Now what am I supposed to think of this? Fine, I'll get back to you. But I think you got the idea how what is happening exactly. If preset and clear, both of them are not 1, then you'll have problems. You'll have to look into it. I will look into what these dashes mean specifically. Does it mean it's complement or something? And here also you have circles. So I'll look into it later. I'll get back to you. But I've given you the basic idea as to how the graphs are affected. Okay, these are all summaries. You can look into the summaries. You have okay, truth table is basically all combinations. Excitation table. This is like your TOC, no? This is almost like your TOC. You have the current state, you have the next state, you have input values. It's like TOC. In excitation table, we want to see from Q to Q next, what are the inputs that I need. But in truth table, it's like given SRQ, what is going to be my Q next? That is your truth table. In excitation table, let's say I want to go from Q to Q next. What are my inputs? What input is needed to go from Q to Q next? But in the truth table, both of them are almost the same, but you're arranging them differently. In a truth table, it's like I have S, I have R, I have Q. What is going to be my next state? It's just rearrangement, I guess. I don't think there is much difference. So basically TOC happening here. You have TOC going on here. So Q has basically two states. Q has 0, Q has 1. From 0 to 1, how will you go? 0 to 1. So you can go with 1, 0. From 1 to 0, how will you go? You can go with 0, 1. From 0 to 0, how will you go? X means either 1 or 0. So you can go using 0, 1 or 0, 0. That is what is there. 0, 0, 1 or 0, 0. So basically TOC. You can apply your TOC knowledge to draw all these state diagrams, excitation tables, truth tables. JK. Okay, let's see. In SR flip-flop with a control input, S equals to 1 means a set, R equals to 1 means reset. And if both of them are 0, what is happening? Memory state, no? If both of them are 0, you're getting memory state. R equals to 1 means reset. S equals to 1 means set. If S and R are 1, we are not bothered. So don't care. We don't want this. So we don't care what happens to the next state. Because we will not be giving this as input. JK flip-flop. If both of them are 0, it means it's a memory state. So Q becomes... Q will remain as it is. Q next will be Q. If K is 1, you're resetting to 0. If J is 1, you're setting to 1. If both of them are 1, you're toggling, right? If both of them are 1, 0 becomes 1, 1 becomes 0. That is toggle. That is JK flip-flop summary. Let's see. Okay, the state diagrams. Okay, these equations you will get using your K maps. You can make a K map out of this truth table, right? Like J, K. You've seen some example. It's there in the slides. You can see K maps. I mean, you can write it directly also. No, if no, can you write it directly? I mean, just do a K map. It should be simple. And all of this is when clock is 1. If clock is 0, I think you will still be in memory state. T flip flop, even more simple. You have if you have 0, it means you're simply retaining the value. If you have 1, you're toggling it. That is your T flip flop. If you have, okay, state diagram. You have two states. Nice. You can obtain this using the K map from this truth table. Okay, more summary. Just put everything in one place and then you have the summary. Interesting. This is PPT 10. It took 2 hours. 2 hours. My goodness. Okay, let me try going to the other one. Let's see how long will this take. Let me not try to go into detail. Let me just finish it fast. I think I've been using the same dialogue for I don't know how many videos, and then it just never happens. Always becomes too long. Okay, flip flop, they store D flip flop. Okay, nice. Asynchronous inputs, preset and clear, we remember. Multiple flip flops. Okay, multiple flops. I think that is what register is, I guess. We'll see. I think if you put multiple flops to. Okay, yes, so multiple flops, if you put in one place, it becomes a register. They'll be performing some actions. We'll see what those actions are. Shift register. So this is one kind of a register that performs a certain action, and that is to shift bits, I guess. So you just shift, left shift, right shift, rotation, that is also there. Parallel transfer. Many bits transfer at the same time. Okay, that is also one way. Parallel transfer. Okay. Nice. Okay, so each flip flop stores exactly 1 bit. So if you put n flip flops in one register, it stores n bits. And flip flops require a clock because positive edge, negative edge, all of that is there, no? So it requires a clock. So all the flip flops in one register follows the same clock. Shift register is a special kind of register. It just shifts bits, either left shift, right shift. There is rotation also, left rotation, right rotation. So if you have n bits stored in a sequence, you can shift them left, right, or whatever. We'll look at examples. So level sensitive are basically your latches, your SR latch with control input, your D latch, and all those. Okay, so this is our first register. Let's see what is this register doing. I see D flip flops being used. I see four D flip flops, no? So nibble is 4 bits, I guess. So holds 4 bits of data. Loads in parallel on clock transition. Okay, let's see what is happening here. You have 4 inputs, I0, I1, I2, I3. You have a clock. You also have asynchronous input called clear, no? Yes, you have clear. So it acts like a reset button, the clear. Irrespective of the clock, it's going to reset. We just kept the option. Okay, what is happening? I0 into a D latch. So when clock is 1, let's assume this is a positive. I think this is a positive edge triggered flip flop. So when clock goes from 0 to 1, that's when this data gets copied. So A0 becomes I0, A1 becomes I1, A2 becomes I2, A3 also becomes I3. Because that is the work of the D flip flop, no? whenever whenever a positive edge comes, your data is copied. So whatever is the input is written into the output. And if clock is not 1, it means there is no change. If there is no positive edge, there is no change. It's going to retain the same value irrespective of the input. I think this is a simple register with parallel load. So basically, you're writing 4 bits of data into the flip flop. That's what you're doing here. And in case you want to reset the entire thing, you can send a signal, and then this will send a signal to all the 4 flip flops, and you can reset the entire data. Clear, essentially. Okay, something is increasing in complexity. Register with load control. Okay, let's see what happens when load is 1. We'll try to make sense, because if you look at the right side looks like this register with parallel load. Let's look at what's happening on the left side. You have all these OR and AND gates. If load is 1, your inverter is there 0, 1. Okay, then what will happen? This is 0, this is 0. 0 and anything is 0. So here you get 1. 1 or anything is 1. Here you get 1. Here you get 1. Here you get 1. Here also you get 1. 1. Here 0, 0. What exactly is happening here? 0, 0, 0. So if you have 0, 0 and 0 is 0 only. 0 you'll get here. Wait, did I make a mistake here? There's no... Is this 0 here? There's no 1. 0, 0, 0, 0, 0, 0. 0 and anything is 0, so you get 0 here. Let's look at I naught. I naught is here. I naught and 1 is I naught. So I naught or 0 is I naught. Here you have A naught. I1 and 1 is I1. I1 or 0 is I1. Here you have A1 as a feedback. Previously there was no feedback. Here we have feedback. I2 and 1 is I2. I2 or 0 is I2. You have a feedback of A2. I3 and 1 is I3. I3 or 0 is I3. You have a feedback of A3. So all of this is happening when my L is 1. When my L is 1, what is happening is the inputs of each flip-flop is exactly I0, I1, I2 and I3. And if clock becomes 1, what happens is these inputs are going to be written into A0, A1, A2 and A3. Because that's how a D flip-flop works, no? When clock is 1, when my clock, let's say this is a positive edge triggered, when my clock goes from 0 to 1, my flip-flop gets triggered and copies the values, copies the input into the output. That is how a D flip-flop works. All of this is happening when my load is 1. Let's say my load is 0. If my load is 0, here instead of zeros I'll get 1, no? 1, 1, 1, 1, 1. This is 0, 0, 0. I think I can see where this is going. 0, 0, 0. So 0 and anything will be 0, and here you'll get 0. 0 and anything will give you 0 here. 0 and anything will give you... If the text is too much on this slide, you can try putting it on paper and see where this is going. 0 and anything is 0. And here what is happening? There is a feedback, no? A0 is giving feedback to this one. And here what is happening? 1, 0. So this becomes 1 here. This also is 1. So A0 and 1 will give you A0. So instead of I naught, you're getting A naught. You can see the pattern. When my load is 1, here I'm getting I naught. When my load is 0, I'm getting whatever is the previous state. So this is how you're controlling your data. Now, irrespective of the clock, when my load is 1, that is only when I will allow my inputs to come and sit here in front of the D flip-flop. But if my load is 0, my I naught will not come here. It will simply be my A naught going in circles. So it's like you have more control here now. It's not like only when there is a positive edge trigger, or that's only when there is a transit. So you get my point, right? When the load is 1, you're allowing the input to come and sit in front of the D flip flop. And when the clock goes from 0 to 1, that's when your flip flop is going to write the values. Let's say you don't want your flip flop to write the input values. So what do? You stop the input. How do you stop the input? In this case, you set load to 0. If you put load to 0, what will happen is A naught will keep going into the input and coming as the output. So it will be just A naught, A1, and A2 going in circles. Nothing will happen. So you're retaining the values. It's a kind of a memory state. You're retaining the values when load is 0. So old data reloaded onto the next positive clock edge. You get my point. So they've summarized it in few words. So I don't think there is any other way to implement this. So that this looks complicated, but it's repetitive. So I think it's simple. If you understand what is happening in one block, you can copy that and put it to A1, A2, and A3 as well. It's just repetition. It looks big, but it's essentially this small part only. This is what you're repeating here everywhere. So which register is this again? Register with load control. Here you have no control. If your input is there, it will be written into the output whenever a positive edge is triggered. But here you have control. Your input will only be written when positive edge is there, and even load control should be 1. Even that should be 1. If it's not 1, it won't be written. Only the same old values will be retained. To get that control, you have to add all these extra gates. That's the only complexity in this. Okay, new kind of registers, shift registers. Cascade means it looks like this. It's joined. The input of one flip-flop becomes the output of one flip-flop becomes the input of the other flip-flop. So if you connect them like this in a chain, it becomes a cascade. Okay, how does this become a 4-bit shift register? How does shifting happen? Let's see if there's an example. Okay, this table is nice. So what is happening here? Let's look at the table. It's the same thing, no? Here there are 4 flip-flops. Here there are 2 registers with 3 flip-flops each. And I'm assuming they're positive edge. Yes, let's assume they're positive edge flip-flops. So let's say initially my register X has 101. So let's say there is 101 and this has 000. So now let's say a positive edge is triggered. And here 0 is also there. Here 0 is always there. Let's say a positive edge is triggered. What will happen when a positive edge is triggered from this clock? When a positive edge is triggered, what will my D flip-flop do? It will write down the D value, no? Yes. So it will write down the D value. And 0. If it writes down the D value, what is going to happen? My 0 is going to change this to 0, no? When there is a positive edge, my first flip-flop will become 0 because my input is 0 here. It's going to override the output. Wait, before I do that, let me also write when the event is not triggered, let me also write what are the outputs of each flip-flop. the outputs of each flip-flop is essentially the state it's currently holding. So the first flip-flop has state 1, no? So 1 will be the output. The second flip-flop has 0 as the output, so state 0 is the output. State 1 is the output. 0, 0. Here output is 0. There's no line, but it's fine. The output is 0. So whenever there is a positive edge, I told you, no, if there is a positive edge, what will happen? All the inputs are going to overwrite the flip-flops. So this 0 will overwrite 1 as 0. This 1 will overwrite 0 as 1. This 0 will overwrite as 0. So basically, everything is overwriting every other thing. So 1 will overwrite 0 as 1. So 0 overwrite 0, 0 overwrite 0. So finally what you'll have is, you'll have, what do you have? You have 0, 1, 0, 1, 0, 0. So let me write it fresh. Let me write it afresh. You have 0, 1, 0, 1, 0. Okay, let me write here 0, 1, 0, 1, 0, 0. And you still have this 0. It's still there. It's a static 0. It's not going to change. So this is what happens after your first positive edge. So this was your initial state, and this is your condition after your first positive state. If you notice, if you can look at the pattern, there has been a shift to the right side. Let's say another positive edge comes. What is going to happen? So this 0 is going to overwrite the value 0. This 0 will come here. This 1 will enter this flip-flop. This 0 will enter this flip-flop. This 1 will enter this flip-flop. This 0 will enter this flip-flop. This has nowhere to go. It will be here only. So now you got new outputs. So what are the new outputs? You got 0, 0, 1, 0, 1, 0. So your next condition is that only. You get 0, 0, 1, 0, 1, 0. Now I think the pattern is very much obvious. You are currently observing a right shift. So my numbers from the X register are moving towards the right register. I will do it once more. Maybe then you should understand. So there is still a static 0, and my 0 is inside this flip flop, so that will be the output 0, 0, 1, 0, 1, 0. Now at the next positive edge, what is going to happen? My D flip flop, the inputs of each flip flop are going to override, no? So this input is going to override whatever is here. So this comes inside, this comes inside, this comes inside, this also goes inside, 0, 1. So finally you have 0, 0, 0, 1, 0, 1. This is assuming you've understood how does a D flip-flop work. Whenever there is a trigger, the input will overwrite whatever is stored inside the flip-flop. It doesn't matter what is there previously. If the input is 0, my output will be 0. Like it will 0 will be stored inside. If 1 is the input, 1 will be the output. And now my output also will get updated. So finally what is happening? You're seeing a shift register because it's arranged in this pattern. So this is basically a shift register, right shift register to be specific. I mean, you're using 2 registers. You can, I guess, just use 1 register. You get the point now. If you cascade your flip-flops and arrange it in a way where the output of one flip-flop is the input of the other flip-flop, you can observe a shift. So if you store anything here, that's how it is going to be. So if you store, let's say 1, 0, 1, 0, depending on what is the serial input, your shifting will happen. Okay, this is slightly different from this one. If we look at this one, let's say 1, 0, 1. Is it different? Let's say everything is at 0 here. And you give 1 as an input. At the first positive edge, what is going to happen? Where was I again? Okay, shift register, no? Let's say my input is 1010. Let's say I'm giving it like this. Wait, which way am I? Okay, let's say I will give 1 and then I'll give 0, then I'll give 1, I'll give 0. I'll give my input like this. And let's say my initial states are at 0. Let's see what's going to happen. So when I give 1, nothing is going to happen. I have to wait for positive edge. Let's say positive edge occurs in the clock. Then let me also write the outputs. Wait 1 minute. Then what is going to happen? My inputs are going to override the output. So 1 is going to come inside 0, 0, 0. So now I'll have new outputs, new inputs, new outputs, whatever. So my new outputs are here 1, 0, 0, 0. Because whatever is inside will become the output. Now I've given 1 as my input. Now I'll give 0. I'll give 0 as my new input. Now at the second positive edge, what is going to happen? At the second positive edge, my input is going to overwrite my flip-flops. Whatever is stored in flip-flops, they're going to be overwritten. So what's going to happen? My this 0 will make this 0. This 1 will make this 1. So I don't have to worry about what is there. So we'll get 0, 1, 0, 0. My outputs will now change. So outputs, whatever is there are the outputs. Now I've given 2 inputs. I'll give one more. Serial input is basically this. You're giving it one by one. So let me give 1 again and wait for a positive edge. And let's say a positive edge appears. So what will happen? This will become 1. So basically everything will get overwritten. You will get this will become 1, this will become 0, 1, 0. My outputs and inputs will change. So in a flip-flop, if 1 is stored inside, it means output is also 1. 0 is the value stored inside, so essentially 0 is the output. Because output is basically the state queue. So you get 1, 0. Now I'm giving my final bit as an input 0. Now after the next consecutive positive edge, what is going to happen? Overwriting. So 0 will come and make this 0. 1 will enter this and make this 1. Get 0, you get to 1. Now you get new outputs. You will get new outputs. So whatever is stored inside will be your outputs. I have nothing else to give, so probably my input will be 0. And my story will continue. If you notice what exactly is happening here. Here what is happening is you've given, this is the order in which you've given, no? First you've given 1, then you've given 0, then you've given 1, then you give 0. So if you notice that they're shifting continuously. It was like this, then it became like this, then 1, 0, 1, then 0, 1, 0, 1. Then it will keep going. It will become 0, 0, 1, 0. It will keep going to the right. So you see the shifting happening, no? Like the data is getting transferred from left side to right side. Essentially shifting is occurring from left side to right side. You can try your own example, maybe make it more clear. Okay, this was serial transfer. We are transferring information from X register to Y register. That is what we did here. essentially shifting from left side to right side, but they're two different registers. Maybe you can think of this as a variable x and variable y. You're trying to assign this value to this variable value to this variable, something like that. Very low level understand. Okay, fine. So shift transfer between two registers. This is shift register, essentially shift register. We're looking at different kinds of shift registers, I think. Pattern recognizer. Pattern recognizer. Combinational function of input samples. In this case, recognizing the pattern. Okay. So this is very similar to your this one, your original shift register. But what exactly is happening here is, see, let's say your pattern is something like 1101. So you will give input like this. No, first you will give or let's take this example only. Let's take 1001 as an example. So you'll give input like this is from, I think you'll give input from MSB, no? So let's assume you're giving input from MSB. So this is your first input, this is your second input, this is your third input, this is your fourth input. So one by one, first it will be 1, then this will be 0, then this will be 1, this will be 0. Like whatever we did here previously. Here we gave the input one by one, no? Here also let us give the input one by one. This is interesting. Not very interesting, but interesting. Interesting enough, I guess. So let's assume everything is at 0 initially. And if everything is at 0, outputs are also at 0. If you notice, there are 1, 2, 3, 4 new lines. And finally, there is an AND gate also. If you remember minterms and all of those things, you can understand this AND gate will give true only when you get when you get here 1, 0, 0 and 1. Only if this combination is achieved will you get 1 out of this AND gate. Because if you see, 1 will come here. If 0 is there, inverter will make it 1. If 0 is here, inverter will make it 1. If 1 is there, 1 is 1. So 1 and 1 and 1 and 1 will make it 1. Any other combination will result in 0 output from this AND gate. Because AND gate, no, everything should be true. Or if any one is false, then you won't get true as the result. Now you can see the pattern, right? This pattern is, what do I say? You see where this is going, no? If 1 is there, simply put one line here. If 0 is there, put a line along with an inverter. And finally join all those lines to an AND gate. Whenever that pattern is loaded onto this register, only then will you get 1. And if you get 1, it means the input is equal to the pattern here. Because what exactly is happening here? Here you are shifting the entire thing to the right. So how this works is, let me say this is 1, 2, 3, 4. So 1, 2, 3, 4. Initially all of them are zeros. Then you will give 1 as the input. Then it will get shifted. This all got shifted, no? Then it will get shifted. And you will give 0 as the input. Can I go down? Yes. Then in the next positive edge, this will also get shifted. So this will go here. This will go here. You will give, what is your next input? Your next input is again 0. After 1, you will give 0. Then you will give 0 again. In the next positive edge, this will get shifted. We saw why it will get shifted. We did it in the shift register part. We saw here why shifting is happening. What is your last input? Your last input is 1. So last input is 1. When this combination is loaded onto this register, this AND gate will immediately give 1 as the output. So that is how you recognize, oh, my table is already here. I didn't have to draw this. So after, when this combination is loaded onto the, wait, sorry, not in. This is my 1, 2, 3, 4. So when the combination is loaded onto my register, my 4-bit register, my AND gate will give you 1. This is basically your shift register, but you have some extra lines checking whether you have a certain combination or not. Here specifically 1001. So this 1001 might be misleading, but the first input value will be your MSB. Your last input value will be your LSB, your least thing. So it's going like this. So let's say 1101 is the pattern that you're looking for. First you will send the MSB. So it will go like 1. Then you will get what will you get? This will get shifted, no? 100. Then your next input is 1. Then it will get shifted. Your next input is 0. Then this will get shifted. Your next input is 1. That's how it is. So if you notice, it looks like it's reversed. So maybe if they gave this example, it would have been much more clearer, because 1001 is very much misleading. Your MSB is here on the right side, contrary to our natural understanding where MSB is on the left side. Fine. This is what pattern recognizer. Universal shift register. Interesting. I mean, if you understand how this works, it should be nice, I think, because in the tutorial they simply asked you to draw the universal shift register. So there's no telling if this will not come or something. Might come, I don't know. Can't say. It's in the syllabus. Okay, I'll tell you what is happening exactly. Do you people remember what does a multiplexer do? So multiplexer essentially, this is 4 cross 1 multiplexer, no? So 4 is nothing but 2 square. Is that how it works? I guess, because here you have 2 power n, and then here I think you have n inputs. I think that is how it works. Yes, so here you have 2 power n cross 1, and here you will have n what were they called? Selection inputs. They had some name, I don't remember. So you have some selection inputs along with your normal inputs. Okay, fine. So yes, so 2 square normal inputs, so 2 power n, and n is equal to your selection input. If I think you should read about multiplexers. You will understand what I'm talking about. So you have 4 multiplexers. What does a multiplexer do? Depending on what your S1 and S0 are, it will decide which input should I send to the output line. It won't do anything. It will directly send the input to the output. But depending on the min term of S1, S0, it will decide, should I send 3, 2, 1 or 0. If S1, S0 is 0, 0, then it will decide to send whatever is at 0. If it is 0, 1, it will decide to send whatever is the input of 1. If it is 1, 0, my multiplexer will send the second input to the output. If it is 1, it will send, if both of them are 1, it means, so basically binary representation to decimal representation. If S1, S0 is 1 and 1, it will send my input line 3 as the output. So this is the basic understanding of a multiplexer. Enough with the multiplexer discussion. So universal shift register. Now I know what does my multiplexer do. So let's suppose, and here for some notation, these arrows are basically, you have S1 and S0 here also. So instead of writing again and again, they've just given arrows. There is no extra output. Bear in mind, it's not an extra output. My multiplexer only has one output. These two are not extra outputs. It's just misleading. There's no output here. This is basically telling that S1 is also here, S1 is also here, S1 is also here. Bear that in mind, please. There are no extra outputs to a multiplexer. There is a single output to a multiplexer. Fine. So you have 4 multiplexers here. Let's suppose S1, S0. Both of them are 0. So what does it mean? If S1 S0 is 0, every multiplexer in this page has to send input line 0 as the output. It has to send input line 0 as the output. So 0 will go here. 0 is going to become the output, my 0 input line. So now let us analyze what is on this line. Here A3 is there. If you follow this line, A3 is here also. So it means A3 is the input, A3 is the output, A3 is the input. So whenever there is a positive, is this a flip-flop? D flip-flop. Yes, this is a D flip-flop. So whenever there is a positive edge, here I will get a change. What is it? Input is A3. So A3 will overwrite A3. So essentially there is no change. So if you notice, when my S1, S0 is 0, everywhere I will retain my same state. I don't have to write it for everything. You can understand, I guess. A3 will remain A3, A2 will remain A2, A1, A0, and so on. They will remain as it is. And if you look at the other wire also, for example, here A3 is there, no? A3 is also going here. A3 is also currently the input of the first input line of this multiplexer. But is anything going to happen? No. Why is anything not going to happen? Because this input is not joined to the output, so no change is going to happen. Now only input line 0 is active across all multiplexers. So it doesn't matter what is happening to the other input lines of every other multiplexer. So we are safe. All that is happening is circling. A3 is going here as input and coming as output. So basically retention, memory state. So essentially when you have S1, S0 as 0, 0, it is a memory state. So memory in the sense, is there a name for that here? I don't know. So 0, 0 is essentially you're just, nothing is happening. You're retaining your previous memory. Whatever you had, whatever were your initial states, they continue to remain as your present states. Fine. So this is when S1 and S0 are 0, 0. Let's look at the other case. Let's say my S0 becomes 1. Now what is going to happen? So according to this multiplexer logic, what's going to happen? My input line 1 is going to get active and it's going to join the output line. It's going to become the output line. My input line will reach the output. Fine. So now what is in this input? If you look, I'll start from A0, or no, I'll start from here only. Okay, I'll start from A3. Serial input for shift right. Does this look familiar? Serial input. If you look at a shift register, you have something called the serial input. Like one by one, you keep giving input, no? One by one. One by one, you keep giving input. Every clock cycle, you keep giving input. That's your serial input. One by one, you keep giving input. So similarly, in a universal shift register, there is some place where you can give input one by one. So let's say you have like 1 0 1 1 0 1, whatever. You have some input. You can give it one by one here. So what is the point now? What is the point of giving? Okay, let's say you're giving only one bit. Let's say you're giving just one bit as input. And it says shift right. We'll see why is it right shift. We'll see. Let's say you're giving, I'll not say 1 or 0. Let's say you're giving X as input. X is either 1 or 0. Doesn't matter. So X is going inside this multiplexer. It's going to come as the output. Now it's going to sit outside this flip-flop until what? When the clock becomes, when the clock gets positive edge, then my flip-flop is going to write this X into A3. Right? So let us wait until the positive edge. Let's see what happens in the other flip-flops as well before this positive edge comes into the picture. Here X is sitting outside, no? Let's see what is sitting outside the other flip-flops. If you pay attention, A3 is sitting here, no? A3 is going to go here. And if you notice, A3 is nothing but the input of the first input line of this multiplexer. So what is going to happen? It's simply going to go inside. A3 is going to go inside. Will come here, and A3 will sit outside this flip-flop. Similarly, A2 also will go inside this multiplexer and sit outside this flip-flop. Similarly, A1 will also go inside and sit outside this flip-flop. Do you see the change now? See, A3 is getting, basically right shift is happening. That's why right shift. So all of this will sit outside until, wait, what is happening to A0? A0 is going nowhere. A0 is just, it's not going to any active input line. It's going to 0 input line, but it's not active. Here the active input line is 1. The input line 1 is active for every multiplex, so it doesn't matter. So now what is going to happen? Now when the clock gets a positive edge, now the flip-flops are going to get overwritten. So my new values are going to be X, because X is going to override this. My A3 will override this when there is a positive edge. Similarly A2, similarly A1. Now if you notice what just happened, A3 got shifted, A2 got shifted, A1 also got shifted. A0 is overwritten, the memory is lost, A0 is not recoverable, it's gone forever. And whatever you gave as X, whatever you gave, the input X basically, whatever you've given here becomes your MSB or whatever. So right shift, how does right shift work? You send everything to the right, but something has to occupy the space for MSB, no? So that one you've given as an input. So all of this happens when you keep S0 as 1. This is what happens when you give S0 as 1. So this is nothing but right shift. You have a right shift occurring when you have S0 as 1. I think now it's fairly obvious to guess what's going to happen when my S1 is 0. When my S1 is 0, you'll get left shift. I mean, you can look at it. I will not, fine, I'll just write here left shift. I'll show you left shift also. And in left shift, what is going to happen? You will give input for the LSB and my MSB is going to disappear. Let's see what happens when S1 is 0. When S1 is 0, S1 is 0. So if S1 is 0, S1 is 1 and S0 is 0, it means number 2. So input line 2 is going to get active. Input line 2. What is in input line 2? So I will start from, this is left shift, no? So, okay, I'll start from here. Yes, so this is active, no? So you will, let's say you're giving Y. Let's say you've given Y. So Y goes inside. Y will sit outside the flip-flop. Let's look at what the other values are doing. So A0 is here, no? A0 will go like this. If you notice, there is a wire here. A0 is connected to an active input line. So this input line will carry this A0. It will go inside and A0 will sit outside this flip-flop. It's going to wait for that positive edge. Similarly, A1 is also going to sit outside this flip-flop, A1. And similarly, A2 also. It will follow this line and sit outside this flip-flop. And now suddenly when there is a positive edge in the clock, my flip-flops will get overwritten. Whatever is the previous value is going to disappear and I'll get my new values. What are my new values? I get A2. I get A1 is going through this flip-flop. A0 is there. And here LSB I've given a new input so that Y is going to get stored here. So if you notice here what just happened, A0 got shifted, A1 got shifted, A2 got shifted, A3 got yeeted out of this picture because it is MSB, there is no other flip-flop on the left side, so left shift just basically made A3 go into thin air, it just disappeared, it's gone. So this is basically your left shift. Interesting, no? Very much interesting. So why is it called a universal shift register? It's doing left shift, it's doing right shift, it has a memory state to just store the values and not shift anything. And if you notice, there is also a clear option, your asynchronous input, that is also there. So if you give clear, if you give one signal, it's going to get cleared. Every flip-flop is going to get cleared, irrespective of the clock. You have that option also here. Your wish, you can add preset also, but it's not given, so don't add. So clear is there, clock is there. We looked at right shift, left shift. I guess reading and memory is essentially the same, I guess. Control, control, yes. Control input. So S1, S0, I guess they're your control inputs. Through S1 and S0, you decide which mode is happening. Is it memory? Is it right shift? Is it left shift? This is how you decide. Using S1 and S0, you decide what is your universal shift register going to do. Okay, now let's look at the case where both of them are 1. What's going to happen when both of them are 1? When both of them are 1, your input line 3 is going to get activated on all in all multiplexers. So let's look at input line 3 in each of the multiplexers and we'll see what's going to happen. Input line 3. I think input line 3 is simple. It's just you'll see. So input line 3. So this 3 is going to the output. Now let's see what is the input of input line 3. I3. Now we are using these inputs I0, I3, I2. So what is going to happen? So I3 is going to go inside and sit outside this flip flop. I2 will sit here. I1 will sit here. I0 will sit here. All these inputs are sitting outside each of the flip flops. Now when you get a positive edge trigger, my inputs are going to parallelly overwrite all the other existing bits. So A3 is going to disappear, it will become I3, A2 will disappear, it will become I2, A1 will become I1, A0 will become I0. So they gave parallel because all of this is happening simultaneously. Simultaneously, all the inputs are overwriting all the data in these 4 flip-flops. So this is called writing. Is there writing? Or loading, you can call them loading. So loading, writing, whatever. So parallel loading. So this is called parallel loading. You're parallelly loading some data onto the flip-flops by overwriting the existing data. So this is your universal shift register. In the tutorial, in the last question, I think they asked some question, I don't know, last or something. At least in Pooran sir's tutorial, they told us that make a universal shift register that has a memory state, that has a parallel loading, that has a right shift rotate. They told rotation is mentioned. Instead of simply right shift, they mentioned rotate. So how do you make this change? Making rotation is very simple. You just have to add just 2 more lines without any gates. You will get your rotation. So what exactly is happening is, let's look at left shift. So what does rotate mean? So when you say left shift rotate, my left shift should happen normally and my MSB should become LSB. That is rotation. So I think you got 50% of the idea here only. When I say my MSB has to become LSB, I just have to make one more line. So in a left shift, what is happening? Left shift is, what is this line? 1 0. 1 0 is 2, no? This is left shift, no? In left shift, A0 is going here, A1 is going here, A2 is going here. Now in order for rotation to occur, A3 has to go to, wait, is this the right one? No, wait. My bad. So A0 goes here, A2 goes here. Yes. Is that how it is? Yes. My bad. So this is your left shift. But now there is no line joining A3 and the input of the rightmost multiplexer. So that you're supposed to make a line. So how do you make a line? Just add some, just make a new connection. So there is no longer this serial input. You don't need an extra input. Just connect this with this. Done. Your job is done. So here you have a connection. You don't have serial input. So now you made rotation possible, because now what will happen is A3 will now go through this line. It will go inside. It It will go and sit outside this flip-flop now. Now rotation is possible. Okay, so this is how you accomplish rotation in left shift. So right shift rotation is very simple. You just add one more line. I'll keep this line here. So this is my left shift rotation line. And because of this left shift rotation line, I'm not taking any left shift input like we did in our original universal shift register. Okay, done. Let me, okay, whatever, something is there. Okay, now right shift means input line 1. So input line 1 will be active. It will join with the output. Nice. So what is happening? Left shift, no, right shift. Right shift means what is this happen? What is happening here? This is going here. It's going like this. If you're wondering why is it not going here and why is it not going there, it can go anywhere, but then all the other input lines are inactive. So there is no change is going to happen. There is no effect. There is no net effect or whatever. Like this will go here also, but nothing will happen here because this input line is not active. Now currently input line 1 is active. So wherever input line 1 is there, you can see any effect there. So here also it will go here. Nothing is going to happen here. Nothing will happen. Here also it will go here. There's nothing is going to happen. Wherever it's possible, it'll go and sit outside. But I'm only following the lines where the input lines are active. You get my point, right? So anyways, so right shift A1 will go and sit like this. It will go outside. So right shift, no, what will happen in right shift? My LSB is going to disappear. So in order to save my LSB, what I'm supposed to do is I'm somehow supposed to join A0 to this input. And I have to get rid of this extra input. I don't need this. So what am I supposed to do? Just make a new connection. No, just make a new connection. Just send this to make a new or A0. No, where is A0? A0. Okay, A0 is coming till where? A0 is coming till here. This is A0. This is also A0. So A0 has to simply go where? Just somehow just make it neatly in your paper or wherever if they ask you, or look at my tutorial once, it's there. So just connect A0 to this and you don't need this extra input and we are done. You get your right shift rotate. You get a rotation option because now my LSB will become MSB because that is how rotation works, right rotation. Nice. So this is your universal shift register. I've also showed you how to make this rotation possible, left rotation and right rotation. You just change 2 lines or add 2 lines or whatever. Fine, this is universal shift register. I didn't derive this thing in front of you. I just showed you why each of these lines are necessary so that you remember them better. Like 0 0 is memory. Like 1 by 1 you can build. 0 0 is memory. 0 1 is right shift. 1 0 is left shift. 1 1 is parallel loading. So 1 by 1 you can build this entire universal shift register. At least that's how you're intended to draw it. Or if you can remember them more easily, it's up to you. I don't know. This is how. Okay, shift register summary. Shift registers can be combined together. Okay, data transfer. We saw that XY thing. We saw shift serial transfer. Okay. D flip flops. Okay. 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 Counters. I think counters are fairly simple. Counters basically count, no? So 1, 2, 3, 4. Let's see. Counters are important components computers. Increment or decrement. Okay. Counters could decrease also. Let's see. Ripple. Okay. Let's see if there's any example. I don't remember seeing any ripple counters. Flip-flop output serves as a source for triggering other flip-flops. Okay. Synchronous counters. They're all triggered by a clock. Okay, let's see. Synchronous counters are more widely used in industry. Counters. A register that goes through a prescribed series of states. Okay. Binary counter. Okay, so binary counter is like, I think is, we'll see. We'll look at some examples. N bit binary counter counts in binary from n to 2 power n minus 1. So let's see if n is 2. So 0 0 to 0 1 to 1 0 to 1 1 again to 0 0. So counter, no, it keeps going on, it doesn't stop. So this is a typical counter, I guess. Let's see. Maybe we'll look at examples. Applications, what is okay, nice. Ripple counters triggered by initial count signal. Okay. Synchronous counters. So I think synchronous counters are simple to understand. Let's see. I'm not talking about the diagram. The concept is easy, I guess. All of the flip flops are triggered simultaneously by the clock input pulses. All the flips change at the same time. Okay, so here we're using JK flip flops. Okay. And if you remember, we remember if J and K are 0, it means it's a memory state. If J and K both of them are 1, they're toggle state. Fine. Most counters are synchronous in computer systems. Can be made from value increments on positive edge. So okay, we're using positive edge flip flops. That's an assumption here. Okay, what exactly is happening here? This is a 4-bit synchronous binary counter. Will they tell us how to make one? We'll just look at this binary counter. Count enable. Okay, this count enable is like an enable switch, I guess. Is it? No. This is like a T flip flop. This is exactly like a T flip. This is nothing but a T flip flop. Because you're giving J and K the same input. So this is nothing but a T flip flop. If J and K get the same value, it's nothing but a T flip flop. And when T is 0, it is a memory state. When T is 1, it's a toggle state. Interesting. So if you notice here, so if you consider all of them as T flip flops, here input is T. Here you get T and A naught. So here the input is T A naught. And you have to AND this with A1 as well. So here you get T, here you get A naught, no? So here you get T A naught and A1. So here you get T A naught A1 as input. You AND that as well. If you AND it, you'll get T A naught A1 A2 as the input. And if you AND it again, what will you get? T A0 A1 A2 A3. Okay, we got some input values. How does this work? Let's say T is 1. Okay, 1 minute. My battery is low. Let me just plug my device in. Yes, I'm back. 4% battery. Anyways, okay, if T is 1, what will happen? If T is 1 and if I get a positive edge trigger, what does T equals to 1 mean? It means toggle. t equals to 1 means toggle, no? So this will get toggled, and here a naught is, if t is 1, a naught is the input, and if a naught is the input, what will happen? If a naught is 0, a1 will remain as a1. If a naught is 0, it will remain as a1. And all of this is when t is 1, if t is 1. If t is 1. And if a naught is not 0, it means a naught will be 1. And 1 means this will be toggled. So if a naught is 0, if a naught is 0, then ta naught will also be 0. Then the input of this flip-flop will be 0. It means memory state. So a1 will remain as a1. If a naught is 1, it means 1 will be the input to this flip-flop. It means toggle. So I'm just writing that. Okay, interesting. I think this will go on, no? You just keep writing. Oh, I think the expression will become longer. Let me not write the expression. What exactly is happening here? I think we'll come to this later. We will see binary counters later. We'll see how to make them. We'll understand them later. Wait. Let me just see what's there. Synchronous, the flip-flops are clocked at the same time. We can design these count. Maybe when we make K-maps and all, we'll understand why did we get all of this. I guess. Let's see. I don't know if K-maps are involved in this. Let me see. Flip-flops are clocked at the same time by common clock pulse. We can design these counters using the sequential logic design process. 2-bit synchronous binary counter. Okay, let's make this 2-bit one. We'll think about the 4-bit one later. Using T flip-flops or JK flip-flops with identical JK inputs. Identical JK inputs mean T flip-flops, so I don't think there's much to think about. Okay, I was talking about this n equal to 2 case, no? When you have 0, 0 in a counter, your next state has to be 0, 1 because binary counter, right? 0, then 1, 1, then 2, 2, then 3. After 3, there is no 4 because 4 is 1, 0, 0. So, for this counter to keep counting, you go back to 0. So, after 3, you will get 0 and the cycle repeats 0, 0, 0, 1, 1, 0, 1, 1. Nice. We wrote in a nice table. If this is the present state, then these are supposed to be my next states. Now, here comes the thing. Now, we have to design this counter using flip-flops. T flip-flops will help us because there's a lot of toggling going on. So toggle means best use T flip-flops. Now TA1 is, so basically you're dealing with 2-bit binary numbers, right? So if you have 1 bit, you can use 1 flip-flop. Since you have 2 bits, you need 2 flip-flops. So I will need 2 flip-flops. I am naming them TA1 and TA0. Essentially TA1 will take care of A1 and TA0 will take care of A0. So you're assigning 1 flip-flop to 1 bit because 1 flip-flop can only store 1 bit. Okay, now how do I fill these values? How do I fill these values? So you just look at the transition 0 to 0. So present state is 0. The next state has to be 0. So what does it mean? 0 to 0 is memory state. And to achieve memory state, what must be the T value in a T flip-flop? T should be 0. So that is why here T is 0. No, let me just hide this. Let me write it. So 0 to 0 means memory state. So memory state means T has to be 0. This is for A1, TA1. This is TA2. So memory state means T has to be 0. 0 to 1. 0 to 1 means toggle state. So basically changing, you're flipping the value. Toggling means flipping essentially. 0 becomes 1, 1 becomes 0. So in a toggle state, what will happen? What value of T do you need? You need T equals to 1. 0 to 1. So I'm going to fill this table now. 0 to 1 means toggle state, so you need 1. 1 to 0, again toggle state. 1 to 0 is toggle state, so you need 1 again. 1 to 1, memory state, you're not toggling, you're not changing. So 0. T has to be 0 to get a memory state, if you don't want a memory state. So 0 will transition into 1 when you have T equals to 1, the toggle state. Uh, 1 will become 0 when you have a toggle state. 1 will become 0 when you have a toggle state. If you want, you can see you will get the same 0 1 0 1 0 1 0 1 1 1 1 1. This is how you write the uh, do you want what table? Okay, call it whatever. Two tables. The table for a counter. The state table for a counter. So this is a 2-bit binary counter using T flip-flops. Positive edge. We are assuming positive edge everywhere. Usually. Okay, nice. So now that you know you need 2 T flip-flops, we can design this. So what they're trying to do here is they're trying to write TA1 in terms of A1 and A0. Same is it's like your usual K-map thing only, but here I think this is fairly simple. You can do it directly also. If you notice 0 0 0 1, like if you note, you can notice it yourself. Oh, I see it. This entire thing is the same as this one. So TA1 is nothing but A0. These two columns are same. So TA1 is nothing but A0 because these two columns are same. And TA0 is not even changing. It's exactly 1, static 1. So TA0 is 1. So depending on this, you can build your counter using this piece of information which you obtained from the state table. Now you can build your counter. So JK is there. That is, you can, if J and K get the same input value, it's nothing but a T flip-flop. Right? So keeping that in mind, so let's say, let us try building it ourselves. Can I build it? Let's see. You have 2 flip-flops. I'll use a T flip-flop because they're essentially using a T flip-flop. If J and K is the same, it's nothing but a T flip-flop. And then you have a clock. The counters have to use the same clock in order to stay synchronized. So I have a clock. Okay, so this is, let's say I'm calling this my first, this is my TA0 flip-flop, or yes, this is my TA0 flip-flop and this is my TA1 flip-flop. So for TA0 flip-flop, what is the input? What is my input for the TA0 flip-flop? Essentially 1. I just have to give it 1. My TA0 should be given input 1. So I just have to do static 1. So 1 is simply going inside this. If 1 goes inside this, my TA0 flip-flop will behave accordingly because TA0 needs input 1 for this for A0 transitions to occur properly. A0 to A plus transitions will A0 to A0 plus transitions will occur properly whenever TA0 is only given 1. So this is the flip-flop that contains A0. This is the flip-flop that contains A0 and this contains A1. And the name of this flip-flop is TA0. The name of this flip-flop is TA1. The input of TA0, according to this equation that we obtained from the table, has to be 1. So input is given as 1. Okay, now what is the output of this TA0 flip-flop? What will we get? I told you, right? Whatever is in this flip-flop is the output. Whatever data it is storing, that is the output. So its output is nothing but A0. Right? The output of this flip-flop is A0 because by definition this flip-flop is storing A0. Right? Because by definition TA0 is nothing but the T flip-flop that is storing A0 information. TA1 is storing nothing but A1, the bit. Because how many ever bits are there, those many flip-flops will have. This flip-flop is for bit A0. This second flip-flop is for bit A1. Now it is convenient for us because for my second flip-flop, I need input A0. And I can see that my first flip-flop is giving A0 as the output. So what I'll do is I'll simply innocently just join this and say I am done for the day. And of course here you'll get A1 as the output. I don't know if you'll be using that. Here you'll get A1 as the output, but will you be using? This is your counter. I guess that's done. Yes, so we're done. So JK is there. You shouldn't be bothered by it because J and K are getting the same input. So it's basically a T flip flop. It's a T flip flop. So same thing. I got the same diagram. This is a counter. So the flip flops will keep counting 0, 1, 2, 3, 0, 1, 2, 3 forever. So this is a counter. This will keep going on. Every time they get a positive edge from the clock, every time that occurs, the flip flops get triggered and they change values. So this is your 2-bit binary counter. Similarly, you can build your 4-bit binary counter, I guess, but that had many gates for some reason. I don't know. We'll see. Okay, K maps they do come into the picture. Nice. Just a minute. Oh, I'm back. Apparently, people told me like we've been telling the same thing again and again for the past 2 hours, but I don't know. Maybe someone must have found that helpful. Some people must have found it repetitive, but it's fine, I guess. Okay, 3-bit binary counter. Identical JK inputs is basically your T flip flops, and you can see here they're using T flip flops in the table. So since it's a 3-bit binary counter, 3 bits, so you have 3 flip flops. A2 will be stored in TA2, A1 will be stored in TA1, A0 will be stored in TA0. So what are these values? These values are the inputs to those flip flops. What should be the inputs for those flip flops so that these transitions occur? So if there is no change in the states, then you keep 0. If you have a change in the states, you keep 1 because change means toggle. If it's the same state, it's memory state, you put T as 0. After doing all that, since you have more number of let's say so many things are happening here, so you use your K map, and then for each column you have to make a K map. So for TA0, for TA1, for TA2, for each of these three things, for each of these things you make a K map, and then you can obtain the expression for TA0, TA1, and TA2. Oh, I think this is where the gates come into the picture. If you look at TA2, according to the T map, you got A1 dot A0. So you get an AND gate. So we can construct our own 3-bit binary counter now. Should be simple, I guess. So first we will create our flip-flops. We have 3 flip-flops. One, will they be placed? Okay, let me draw it this way. 1, 2. You have 3 flip-flops. You have 3 flip-flops for each of the 3 bits. I will call this TA0, TA1, TA2. I have a clock that is synchronizing each of these flip-flops. This goes here, this goes here, this goes here. Clock. So I have T here, T, T. What is the input of TA0 according to the K map? 1 is the input, and since that is storing A0, so A0 is the output, and A0 is coincidentally the input of TA1 as well. So I'll just join this A0 as the input of TA1, and output is essentially whatever is the bit it's storing. So it's storing A1, right? TA1 stores the bit A1, so A1 is the output. But if you look at TA2, TA2 wants A1 dot A0. So you'll have to make an AND gate with A1 and A0. You make an AND gate, and then you send that as an input to the last flip-flop TA2. Now this becomes your 3-bit synchronous binary counter. Synchronous because you have a clock, 3-bit because you have 3 flip-flops. And this will do your job. Is that the same? Did they give a diagram? Yes. So A0 is correct only, no? A0, A1, and you get AND gate you make, and then you give it to your. Now this feels slightly infuriating, no? Because they're using T flip-flops and then they make the diagram using JK. Don't worry, because here JK are getting the same inputs, so they're essentially T flip-flops. Do not get confused. The same thing. Both of them are the same thing. Parallel counters. Isn't that what we've been doing? Yes, that's what we've been doing. The nth bit is always complemented. Okay, let me look at an example. 4-bit synchronous binary counter. 1 A0, A1 A0, A2 A1 A0. Okay, so where I am genuinely confused. Note that in a binary counter, the nth bit shown underlined is always complemented whenever. Okay, they told something, but how does the example? I don't know. Fine, I don't know. It seems like an extra piece of information. If it makes sense to you, make sense of it and let me know. I'll also try to make sense of it. So this feels like a pattern, no? So you have you have A0, then you have A0 A1, A0 A1 A2. So that's why you got all those gates. So I think that I think this would make sense now, right? This one. But here you have 3. Okay, fine. There you have 3 AND gates. here also you're supposed to have 3 AND gates, but somehow they did some jugaad, I think. One, see, 1, 2, 3. A2, A1. A2, A1. Okay, they're using and already ANDed value, and okay, fine, nice. Same logic, you can build the same binary counter, same whatever, however we built 2-bit and 3-bit, same way you can build 4-bit binary counter, 5-bit binary counter, how many ever binary counters you want you can build. Okay, now new counter. This is not a binary counter, this is a BCD counter. What is a BCD counter? Initially 0, 0, 0. It becomes 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Okay, fine. Essentially 1 to 10, right? 1 to 10 to 0. So 0, okay, fine, whatever. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0. So this is your BCD counter. Your decimal numbers is but in binary. You can find out. So you need 4 bits because you have Q3. You need 4 flip-flops because you have 4 bits. You'll have to derive the equations. If you're unable to derive it from the table, you have to make K-maps, I guess. Yes. Or is it possible to derive it from the table? Let's see. So I will make 3 flip-flops, 3 T flip-flops, which I'll assign to each of the bits over here. T3. How do I write the equation for T3? T3. Okay, fine. Let me first look at T0. You have to make that state table and all, no? Then only it will become easier, I guess. Like this. This is your state table. It will become slightly big. So that's a safe way of doing it. Or else you can think about it like this. So 0 to 1, 1 to 0, 0 to 1, 1 to 0, and so on. So if you look at it, Q0 is always toggling. So why will Q0 always toggle? It will only toggle if your input is 1. If the input is 1, your T flip-flop will keep toggling. So that's how T0 became 1. Let's look at T1. Let's look at T1. When does T1 change? This is 0. This is 0. Whenever Q0 becomes 1, if Q0 becomes 1, Q1 gets toggled, right? If you notice, if Q0 is 0, nothing happens to Q1. If Q0 is 1, then Q1 gets toggled. Q0 is 0, so nothing happens, the same 1 is continued. Q0 is 1, so Q1 gets toggled. Q0 is 0, so nothing happens, 0 is continued. Q0 is 1, so Q1 gets toggled, and so on and so forth. So I'm trying to derive it from the table itself. If you want to do it the safe way, you can make the state transition table like this. A2, Q3, Q2, Q1, Q0, Q3 plus Q2 plus Q1 plus Q0 plus. Then you can write TA3, TA2, TA1, TA0, and then make K maps and find out your equations. I'm trying to directly write it from the table. This method was discussed in class. So what is happening here? My T1's input is essentially this one. So I should have 1 here. And I should toggle this, no? If I have 1, I'm toggling this. If I have 1, I'm toggling this. If I have 1, am toggling this, here I have 1, but there is no toggle, right? Here if I have 1, there is no toggle, there is 0 to 0. So there is that one case where the toggle rule is not happening, right? Yes, so if you notice here, this toggle is happening when Q3 is 0, Q3 is 0, Q3 is 0, Q3 is 0. Here Q3 is not 0. So this is all. So that's why if Q3 is 0 and Q0 is 1, that is when your toggle happens. So T1 is nothing but Q3 dash Q0. So similarly, you can try experimenting and directly writing down the equations from the table. But if you want to go the safe way, just make your state transition table, write Q3, Q2 and so on, Q3 plus Q2 plus and so on, write your T3, T2 and so on, make K maps, get your equations and say goodbye to the question. So after you get your equations, you can start making your diagram. Essentially, if you have you start from the first flip-flop, input is 1, output will be Q0, and Q0 is used in every other flip-flop, so you can redirect, you can make wires, use AND gates and give the output of one flip-flop to the other flip-flops as input, and so on and so forth. Now for example, this is your T1. T1 gives Q1 as output, and Q1 is used by the other two flip-flops. So it goes on. It's like the output of one flip-flop becomes the input of the other flip-flop. So it goes on like that. So that is how you make your counters. That is what makes it sequential, right? I guess. Synchronous up-down counters. Up-down counter can either count up or down on each clock cycle. Up counter counts from 0 to 111 and then changes back to 0. Down counter counts from 1111 to 0000 and then back to 00. Okay. This is, I think, right side is just an example. Maybe we'll just look into the main picture. Counter clock counts up or down each. Okay. Since we are using flip-flops, the transitions occur only when there's a positive edge or whatever. Up-down synchronous counters. Up-down synchronous counter. A bidirectional counter that is capable of counting either up or down. Okay. An input control line up or down, or simply up specify the direction. Okay, fine. So I think we as a user will have an option to give up or down. So if you give up, it will keep counting up, and if you say down, it will keep counting downwards. So okay, we'll see. Look at an example, 3-bit up-down synchronous binary counter. Such a nice name. So what exactly is happening? So if you have 3 bits, how many numbers can you count? You can count from 0 to 7. So up counting means basically you're going in an ascending order, and down counting means basically descending order, right? Yes, I think. So 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7. That is up counting. 7, 6, 5, 4, 3, 2, 1, 0. That is down counting. Fine. How do I write the equations? Like I think you can do that state transition table, or you could try looking at the table itself and try deducing what the equations are. I think Q0 is the simplest. Q0 is toggling every single time. So Q0 is nothing but 1. The input for the flip-flop TQ0 has to be 1 because it's always toggling. Let's look at Q1. When does it looks like a similar story, no? If Q0 is 1, this gets toggled. Q0 is 1. I'm still up counting. If Q0 is 1, this gets toggled. If Q0 is 1, this gets toggled. If Q0 is 1, this does get toggled. Okay, so when it is up and when it is Q0, TQ1 changes. Right? it gets toggled. Or else, let's say it's not up, we're going down. So down means nothing but not of up. So let's say we're not going up. So if we're not going up, then what would that mean? We're going in the opposite direction. Let's say we are starting from somewhere over here. So if you're going upwards like this, you're going downwards essentially. So if you get a 0, then you're getting a toggle. If you're getting a 0, then you're getting a toggle. If you're getting a 0, then you're getting a toggle. If you're getting a 0, then you're getting a toggle. So it's the other way around. The story is opposite. So you get a Q naught Z, sorry, not plus, Q naught bar. So Q naught dash dot up dash. Q naught bar dot up bar. So any of these two things, they will result in a toggle. So if when up is true and Q naught is true, TQ1 will become true, which means you'll get a toggle, which is essentially what is happening. You're getting a toggle. Or if down is true, then Q naught has to be 0. That will result in a toggle, right? We are seeing that results in a toggle because true will make TQ1 true. If TQ1 is true, TQ1 will get toggled. See, if this is too much, what you do is you simply make a state transition table and then make K maps, and then you can easily get your expressions for TQ0, TQ1 and TQ2. Same, I think, is the story with TQ2 also. That also can be obtained either from the table directly, or you can make your K maps. Might be time consuming, but it's a safe way in case you do not want to break your head trying to get the equations from the table itself. But if you're able to do it, you can do it. Saves a lot of time, I guess. Now that we got the equations, we can make our counter, but we have like two counters in the same counter, up counter and down counter. But there's only one control unit, up. If up is true, it means you're counting upwards. If up is down, if up is false, you're counting it downwards. Okay, maybe they reduced this separately and then just added a plus in between. Okay, you have a set of equations, and building a counter should be fairly simple, I guess. You have a T flip-flop. Your first flip-flop's input is 1. It gives output as Q naught and Q naught dash. Here I think we are using that representation where inverted forms are also taken into consideration, because usually, not usually, like until now we took only this as your T flip-flop, no? Now we are also taking, we are using this as a T flip-flop representation, because we have inverted states. We are using inverted states in the expression. So instead of using inverters and instead of using external inverters, why not just use the already inverted states from the flip-flops themselves? Because if you remember, flip-flops will have the state Q itself along with its inverted state, so you can always use it. You don't have to use an extra inverter. So that's why we're using this form of the inverter, this form of the T flip-flop. In all the other previous cases, we didn't have to use this because I don't think there were any inverted states required. Designing. Oh, this is okay. This is a counter. Okay, they're like use JK flip-flops. Now things get slightly interesting because don't care comes into the picture. Why does don't care come into the picture? Let me just show you 2-3 state transitions, and then you'll understand why does X come into the picture in the first place. So JK flip-flops, for a quick revision: if J and K both are 0, it's a memory state. If J is 1, that is set. If K is 1, that is reset. If both of them are 1, it is toggle. This is JK flip-flop. Now let's look at the first line. 0 to 0 is a memory state because there is no change. Or it could also be a reset state. right? If it is a memory state, my J and K is 0 0. If it's a reset state, my J will be 0 and K will be 1. So both of these J and K values, like both of these pairs, are valid pairs. So how do I represent it using just one pair? So I have to write it 0x. So irrespective of the value of K, irrespective of the value of K, my state transition. So essentially, if it's 0 0, my JK should be 0x. Because the transition could have probably occurred by reset, or it could have occurred because of memory state. So there are two possibilities. Let me take some other random state. So 0 to 1. 0 to 1, there are two possibilities. It could either be a toggle state, or it could have a toggle transition, or it could have occurred because of set. So toggle would occur if you have 1 1. Set would have occurred if you have 1 0. So this is essentially 1x. So that's why you have 1x in this line. Let me look at another example. Let's say it is 1 0. 1 0 means it's either reset or toggle. So reset is nothing but K is 1. So 0 1. Toggle is nothing but 1 1. So this is nothing but x1. So that's why you have x1 here. And if you look at 1 to 1, 1 to 1 is either a memory state or it is a set state. So memory state means J and K, both of them are 0. But set state means you have J as 1 and K as 0. So this is nothing but x0. So that's why you have x0 here. And same is the case with the other two flip-flops and the other examples as well. So this is how you can fill your inputs for the JK flip-flops. Your 3 JK flip-flops, because they've specifically mentioned use JK flip-flops, so you have to use JK flip-flops. And mind you, this is a 3-bit gray code, no? So 0 0 0 0 0 1, only one bit will change now. 0 1 1 0 1 0 1 1 0. You have to you'll have to know how to make this gray code. If you remember in minor one, gray code was asked. I don't know if they'll be like just make gray code. Like you'll have to know how to make a gray code, just in case, if you could remember that. I don't think they'll tell us how. I don't think last time they didn't give us the gray code. We had to remember what gray code was. The sequence of numbers. Only one bit changes in the sequence. Anyways, this is one example using JK, and then you have gray code. Interesting. From this table you can get your K maps, and then you can deduce what the equations are. You have 6 columns, so you'll get 6 small K maps, and using that you can build your counter. You can start from the Q0, and then you can move ahead to Q1 and Q2. Because the Q0 flip-flop, the JK, essentially this flip-flop's output is Q0. So this Q0 is used in other flip-flops. So that's why you have to start with this one while drawing. Counters with parallel load. Okay, counters with parallel load can have a preset value. Load signal indicates. Okay, we saw what does the load signal do. It would indicate whether the data should get inside or not. Clear resets counter to all zeros. Okay, carry output could be used for higher order bits. Is there further explanation? Oh, this is the last thing. Okay, this is the last thing. Counters with parallel load. I think the load part is similar. It's very similar. So I think if load is 1, then your inputs will go and sit outside the flip-flops. If load is 0, then it is simply memory state. No change will happen. Even if The clocks keep oscillating. Even if you get positive edge triggers, nothing will happen. Memory state only will be there. If load is 0. If load is 1, then you will get new input. They will overwrite your old values. So A0 will be replaced with I0, A1 will be replaced with I1, all that's fine. Load is okay. Clear. Where is clear? Clear is here. Okay. Clock is also there. Why is it different? We looked at load somewhere, no? Where is load? Load. Do you guys remember where it is? I don't remember where it is. Fine, I'll just look at A0. I will not go through the entire thing. So if load is 1, count, okay, there is a count, okay, fine. Let me look at the truth table. I think the truth table can help me. If clear is 0, it doesn't matter, right? My output will be 0 only. It shouldn't matter. If clear is 1, so if clear is 1, so nothing will happen, all normal functioning. So I think this means fine. So fine. Not. So clear is like an extra input. If it's 0, then it means put everything to 0. If clear is like 1, it might sound counterintuitive, but that's how it is. Clear is 1, so you'll have to clear everything. No, it's not like that. Just give it whatever name you want. If it is 0, it means the output has to be 0. If it is 1, then my counter will function normally. Positive edge triggering, so what will happen here? Load is 1. If load is 1, then only you will make changes, no? You load your inputs. So the count doesn't matter. That's what this truth table says. The count doesn't matter. If load is 0, what will happen? Previously, when there is no count, you say A0 simply was A0, A1 was simply A1, and so on. If load is 0, okay, let's see what happens. If load is 0, this is 1, this is 0. So everywhere you get 0, 0, 0, 0, 0, 0, 0. Okay, you get 0 in the OR gates everywhere. Almost. Okay, I'll only go into A0, no? I told I'll only do A0. But let's say count is 1. So 1 and 1 will give you 1. 1 or 1 will give you 1. 1 or 0 will give you 1. 1 or 0 will give you 1. JK1 means toggle. So essentially these are essentially T flip-flops, because J and K are again are they again getting the same values? I don't know. They look like, but I don't know. No, I'll not say. So J and K1 means toggle. So A0 will get toggled. Now this looks like a complicated thing. I'm not covering this. Too much work. Let's just stick to the truth table. About the figure, I don't know. Maybe try looking into it. If it makes sense, somehow just look into it. I am looking at this page for the first time, so let me take a while to go to this page. Let's just go to the summary and get over this. Dynamic counters can be ripple or synchronous. My goodness, where are ripple counters? Did we come across ripple counters? Let me know. I don't remember looking at ripple counters. Ripple counters use flip-flop outputs as flop triggers. Some delay with. Okay, we did not deal with any counters that did not take clock as an input. Every counter that we designed took clock as an input. So I guess I don't think we've dealt with ripple counters. Synchronous counters are controlled by clock. So I think whatever counter we've designed, they're all synchronous counters. I think some of them had clear as an extra input, but we still had a clock. Up down counters can either increment or decrement. Okay. Counters with parallel load can be set to a known value before counting begins. Okay, that is what a counter with a parallel load does. Okay, so you can load. Okay, fine. So if load is 1, you will load. That is understood. And when count is 1, you'll keep counting. And if count is 0, you'll stop counting. Interesting. So from this truth table, we can understand what a counter with parallel load is supposed to be doing. But then try going through this diagram. I'll try going through it later. Fine. So this is the end of PPT 11. Took a lot of time, I guess. When did I start? 10, 11, 12, 1, 2. It took me 4 hours. My goodness. Slept, I guess. So I will end the stream now, or let's see if you people want me to continue with the tutorial solving. Let me just see. I will mute myself for a while and I'll just see. I think it's quite late, so I'll just send the stream here. Tutorial I've uploaded anyways, no? So I said if time permits, I'll continue. Time is not permitting as it seems, so I'll end the stream right now. And I'll go have a nice sleep. Good night, all the best. Let me see. Stop streaming.